Ready? I think the most important note I want to make right now is that you can't eat or drink inside this room. So if you got coffee, something like that, then please take it outside. Other than that, welcome. We're going to get started soonish. Thank you.
Kun je nog iets omroepen? Ja? Kun je even omroepen dat ze consumpties is er nu mee? Ja, dat
ik maak net mijn zin af.
Nou, perfect. We waren te laat namelijk. Ja.
Cheers. Ja, nee, dat kan niet. Jasper is helemaal naar de kapper.
Normaal gesproken checken we dat.
You walk around here like you belong. We got this. Serieus? Ja. Maar waar kijk ik nou naar? Kijk ik nou naar hun slide? Ja, ik kijk naar hun slide.
Zij hebben ook een slide hier.
Ja, zij hebben ook een slide. Okay. Als ik slide. Kan je me even switchen naar mijn laptop? Ja, hey. Seeing this as this is a technology thing, most of you will love having some Wi-Fi in case you desperately need it. So here's all the details. It's one of those username and password radius things. You'll get it. Wow, everybody went quiet. I start talking and people went quiet.
Good job.
Are we starting? Is this it? Is this everybody?
I think it's about time.
Wow, that's insane. Okay.
Start?
Let's do it.
Let's do it.
Okay. Hey, welcome everybody. This is RustNL 2023. I can't believe it. I am your host, together with Dirk-Jan Hoffmann. Am I going to introduce you? Maybe you just want to introduce yourself.
Yeah?
What is it that you do? Where do people know you from?
Well, I guess most people here will know me from some open source projects that I help maintain, like a quick implementation and a template engine and a TLS implementation and a progress bar library and some other things. So I guess that's the main thing, and maybe some meetups in the past or conferences. And where do they know you?
No, nobody knows me.
I think they might.
Yeah. I think it's because mostly I'm from the networking industry, so I do a lot of internet-y things. I work at Nelnet Labs. We make software for DNS and internet routing. And 5 years ago, we fell in love with Rust. And then we met some kindred spirits at Tweede Golf. And I think it was about 6 months ago or something, or that Erik Jonkers was like, hey, you want to organize a Rust meetup? So we did like a small one, a tiny one, with 50 people. And it went really well. And we really enjoyed it. And then, Yeah.
It also sold out really quickly.
Yeah.
That's an important part of this story, I think.
Yeah. And then basically they were like, would you be interested in doing a bigger one? And it seems like you can talk. And people have to stop me from talking.
Okay, stop talking about yourself now.
I know. This is basically what happened. So we're going to have a packed day for you. I think one of the most important things I want to say is people love doing live demos. So things are going to go wrong. You know, we're going to have shenanigans with like monitor resolutions, unreadable fonts, and that kind of thing. We try to coordinate all of this and anticipate everything. We're pretty experienced, but, you know, bear with us. This is not one of those things where you get like polished slides from a marketing department. It's all fine. What else?
Let's see. Yes, we have some sponsors that we should talk about. So basically, the big sponsor that made today possible is FutureY. I'm not sure if I'm pronouncing that correctly. Someone? Yeah? So I think they spend a lot of time and energy on Rust, and that's great for everyone because we all get to benefit from that. And we have a bunch of speakers here from FutureY today. Then, of course, there's NLNet Labs, Alex, and we also have a talk from one of the NLNet Labs developers. Tweede Golf, of course, one of basically the staple of Dutch Rust meetups, right? I think they've been involved in most of them, thanks in part to Erik. And then RustNL, I guess I'm technically president of the RustNL Foundation. It's I spend about, I guess, 2 hours a year on it, so not a lot. But yeah, we're here. We used our bank account, so I guess that counts. Then there's a bunch of sponsors, other sponsors, who we'll get to meet later on in the breaks. That should be fun. I know some of these folks too. Alex, what else do you want to say about this slide?
Well, we did a big announcement that Haley Dekkers was going to do a presentation, and unfortunately she couldn't make it. And we hope we found a fitting replacement, but if you're here to see Haley, I'm very sorry she's not presenting today. And then I guess we have a prize. Giving away some signed books, which is something that I guess you would like to talk about.
Yes, so Mara has kindly brought 10 of her books on atomics and locks in Rust. And if you have a name tag with a number on it, you have a chance of getting one of these books. And if you already have the book, then hopefully you have a name tag without a number on it, and you can get your copy signed. And that all happens during the first break downstairs in the forum room, which we'll talk about when we start the break.
And then lastly, so all of the breaks, of which we have a couple, all of the drinks and lunch and that kind of thing, is in the foyer where you entered and registered. And if you want to meet all of the sponsors, of which we have some, and talk about some of the awesome things that they do, that will be in the forum downstairs, one level down. So you walk down the stairs, and on your right you will see another room where all of the sponsors will be.
And that's also where the book signing happens.
Exactly.
All right. So do we have other slides here? Let's see. Well, it's not lunchtime yet.
No, I wish. No, yeah. Yeah, that's it. You
have to do a bit longer without food. So yeah, we're a bit early, but I think I'll start introducing our first speaker.
Absolutely. I'll leave you to it.
First speaker is not currently here. Just left the room, so that's fun.
Perfect timing.
I have to talk really slowly during his introduction. So our first speaker is Rik. Rik has been working on editors for like 15 years. He built editors in JavaScript until he got sick of it. And then he found that was around the time that Rust started becoming more mature. And so he started working on building editors in Rust. And editors is not just like a code editor, it's like much more than that. And Rik is a really fun speaker. I've seen him talk a few more times. And so he will not just show his what the editing is like, but also what you can edit, and that's including like visuals and audio, and all of that written in Rust in a very cool custom stack that is fast to compile, unlike some other Rust programs. So yes. Well, there's much to be seen and heard. So please, Rik, come forward and take it away.
Hello, everyone. Welcome to this conference day. I'm going to talk about Makepad. This is our project, our startup, and we're trying to build a UI stack in Rust. And a very long time ago, when I was building a web-based IDE called Cloud9 IDE, we also built a code editor called ACE. It was based on HTML. And it used divs to render all the text in the code editor, and a virtual viewport, of course, because otherwise you couldn't update it fast enough. And I was struck by how tedious and how stupid it is to try to abuse an HTML render engine for anything other than Wikipedia, essentially. Because it was always in our way. We had designers making the UI designs, and then we had a bunch of programmers who were like, yeah, really? We're already so behind, and you keep adding new UI. We can't process fast enough. So we had a huge bottleneck in our application development. Besides things being so hard that apparently we were one of the 2 companies in the world that were making a text editor in a browser. So that was madness. At the time, we thought it was all right, but I learned that I couldn't do anything. I couldn't innovate the editor because I wanted to do inline widgets. I wanted to do fancy text editing that uses a lot of UI mingled in with the editor. And in a browser, I couldn't do it. One of the things I wanted to do was animated code folding. Animated code folding. Simple thing, you think. Computers have been faster than a Commodore 64 for a while, but in HTML you can't do it. And it's also very hard to control because you deploy on different browsers, and Safari breaks something again, and it is just tedious. So after that startup, I thought, well, let's start over. Let's start from scratch with WebGL. That was just out at the time. You have shader toy. You can see that the GPU is programmable. Shaders are little programs that run on your GPU, not your CPU. And you can use them to transform geometry, or you can use them to style pixels. Essentially, you write functional little programs that run on pixels. And let's see if I can, hold on. There we go. So this was my Makepad JavaScript peak, essentially. This was where I got. So all of this is live coding JavaScript, and this is actually the only structural JavaScript editor that I've ever seen existing. This is essentially an array that has 2 formatting modes. As you type, everything is live formatted. So when you, for instance, I align the objects to the key in the object. It's a feature that is actually very hard to do if you don't have a structure editor that formats as you type. And this is where I had the first idea of writing shaders using the host language, or something that looks like the syntax of the host language. In this case, it's JavaScript. However, I was like, okay, you can live edit everything, everything works. The problem is the performance is just not there if you want to do something complicated. And I had a friend of mine in game development, and he said, like, cool, you made a UI kit. For what exactly? I was like, okay. Yeah, you can't get data into the browser because it's going to just barf on it, or large amounts of data. And it's also very unstable. Like every time I ran these web-based demos, or you had to restart the browser after a few hours or something. It was always, and if you live code in this thing for half an hour at the time, it would just crash Chrome with a garbage collector segfault or something. It was really great because as a developer, you can't do anything about it. You don't have to reach into the platform. You fly in a ticket into the Chrome thing and then hope that somehow it'll get fixed, unless you want to do that yourself, which I did not. So at the time I was like, okay, so maybe it's not just HTML, maybe JavaScript is also the problem. And along came Rust. I spread out over years. But so Eddie, who worked at Mozilla at the time, was is my co-founder. If you have any questions later, Eddie, stand up. I was like, okay, what about this idea of writing a hybridized shader UI, but now let's try to do it in Rust, right? And Rust is fast, very, very fast. I could finally do these things that are not so great in JavaScript, like, for instance, this is a fractal zoomer running in F64, so 64-bit float. And it's using a worker pool with just tiles, just like Google Maps, essentially. It does the tile tweening on the GPU. By the way, if the frame rate hiccups, that's not me. It's the Beamer has a frame buffer in between that is just like messing things up. So I have like smooth 120 hertz here, and you have, I don't know what that is. But anyway, so just so you know, it does run 120 hertz smoothly. And also for UI. So someone in finance was like, can you draw a lot of number markers? And I'm like, yeah. Okay, let's do it. And I was like, okay, let's just update it every frame. They're supposed to be red and green, but they're sort of mixed in between. This is also running 120 hertz. You can actually update the screen again, unlike in a web browser with HTML. So let me get back to our original goal. That I had with building IDEs is that I want to unify programming and design again. Like we had in Visual Basic. I mean, it wasn't much design. You could design a UI, but it was designed for the time. And IDE used to mean that it was a collection of tools. You know, not just a debugger and a code editor. There was a UI designer, icon editor, all these things that were lost to us, essentially, as we moved towards web or other platforms. And so the design goal is that we have a code editor and we have a design tool, and they're stuck on the same code, essentially. So when you move something in the design tool, it updates the code editor in reverse. This is a work in progress. Like we're currently building the visual designer. We've built the entire UI stack, platform abstractions. Code editor's on the way now, the final code editor. I think it's the third code editor that we've written. But because the code editors, doing code editors extendably is actually quite a hard problem. Either way, we decided to build a test UI. This is our test UI. It's a synthesizer. It also plays sound. And then you can, it has all the little bits and bobs in the UI. It's really kind of a fun thing. It's a small synthesizer that a friend of mine has a, this is not rocket science company, he's making synthesizers. He's just like, let's build you a demo synthesizer, and on a few afternoons he programmed the synthesizer that's now also MIT in our code base. But so this is like a fully fledged UI. It's got little graphs. You have a sequencer and a little piano. So the keys on this piano are all pixel shaders. So when you move the mouse, an actual virtual lamp moves straight up over the key so that it shines, and then it moves back down again. You know, you don't fake this with gradients. You can actually do something here that looks nice. Well, as you can see, the preset editor is a work in progress because this required us to really do some design on the APIs, which I will talk about in a bit. And we also made a mobile UI, which I think will it work? It's the same sequencer. Let's see if I can play. And hold on. This is the same UI, or essentially these are multiple UIs running on the same Rust code. RUI language is a DSL that is a subset of that is tokenized in the Rust tokenizer, just like a macro, but it has a different syntax. And one of the things you can do is you can create multiple UIs that bind to the same state. So here you see that when I draw stuff on the thing on the right, it's data bound to the stuff on the left. And this is a way of programming multi-device UIs, essentially. There used to be the responsive thing where you scale something and then images move, but I find that that only really works for pizza ordering apps maybe, or something very, very basic where images can just shift around. But normally when you make a mobile app, you really want to focus on mobile UX. It's not a mouse, it doesn't have a keyboard, it is touch, and it changes the UI. So what you do is you just make multiple UIs and have only one on-click handler, but I'll show that in a bit. And of course, we're finally moving towards our final goal, and that is that the UI is visually designable. So over here you see essentially the outline. This is very similar to what would be your outline in Figma. The font size and the style of this is of course not good. But here you see the desktop app with all the little frames. And here is the component view, essentially. So this UI is built out of components that are inherited. I'll go into that when I talk about the language more. But essentially, you can design a component and then instance that as many times as you want, overriding sub-properties. It is very similar to how CSS composes, except it's linear inheritance. So here we have the Visual Designer, the first prototype of it, where the component model of the whole application is splattered out. Let's see. Yeah, so to do these kinds of UIs, this is just a test of a UI. The other UIs that we test are IDEs, code editors, and essentially advanced UIs that were really hard to write in other systems. The idea is that it's live editable. Rust is a compiled language, but if you put a block in the Rust file that is a different language, you can also ask the application to hot patch it. So that I cannot demo yet. We're working on that. The design tool manipulates text in the code editor. So it stands on the undo stack of the code editor, which is really nice, because then you always have this dual view. You can edit text, just like you would edit XML or HTML, and you can edit it visually. So these slides are essentially a Makepad app. The DSL allows you, the UI language allows you to compose applications. A few days before the talk, I was like, wait, I have a slide widget and I have a UI structure. Why can't I just cut and paste the application instances into the slides? So I just copied our examples, linked it using a crate, imported a widget in our structure, and yeah, now I could run our example application essentially inside a slide as a real application. And it was also a nice stress test, because normally this is the amount of complexity that you have in an application. You just have a single UI. But now it's like, okay, what if I do 5 of those? Or these are all separate instances of the UI. I'm not moving it around. And what's even worse, I would say, is when I scroll, I'm actually regenerating all of the UI, because I didn't optimize it with a viewport yet. And this is so great about Rust, is that you can, sometimes in these situations, you can just be really dumb and get away with it. And in JavaScript, you cannot. So this is running at 120 Hertz for essentially 10 times the UI that we use now. Then I wanted to show you some actual code to give a bit of context. So this IDE is my old IDE. When I started learning Rust 4 years ago, I was like, okay, let's build an IDE immediately. So without any knowledge of Rust, I started building it. And it took me 9 months until I had my IDE that I could use myself, which is still this thing. It is really terrible, except for this one feature that I finally got that I never managed before, which is animated code folding. And it's so fast, it also runs in a browser. This is this is the WebAssembly build of the same thing. So I now, because of this feature, I can never move back to Visual Studio Code again. Because you're like, zoom! Oh no, it's like an impulse trigger. Because I use it to quickly find a function or a structure, and it doesn't fold away the content. So it keeps my spatial awareness of where I am in the code intact. So you can just jump to the middle here. So yeah, let's look a little bit at the structure that we've made for applications. In this case, we have an app RS, which is different from a main and a lib, because Makepad applications need to compile to both a dynamic library and a binary, like an executable. The reason is that some platforms, like Android or WebAssembly, essentially require you to make a DLL or a dynamic library. So that we have like a stub, lib, and main in front of app. So that's why you can reuse it. Then you have a live design macro. This is really just essentially says, from here, it is the UI DSL, just turn it into a string. This essentially gets turned into string minus these little references here. And these are type connections between Rust and the DSL. The macro just puts a type ID of this class inside the list. So that means you can inherit, so this kind of inherits a structure from a Rust object. The Rust object is the base. This is very similar to the original architecture of SpiderMonkey in web browsers, where you would instantiate a JavaScript object with a C base class. So this is the same here. And in this case, we're looking at the slides. So let's look very briefly at the Rust object that we have. Here's app. We have the UI itself, which is a widget reference. It just holds on to the root node of your UI. And presets, it has an audio graph, which is the little audio engine that is doing the synthesizer. And it has some MIDI input. And now you can assign, here we go. Now you can assign to that UI node in the DSL a UI object. If you look at, hold on, that's an important feature part. You see I do derive live here. This is a proc macro that allows you to bind this dynamic language to Rust structs. It's essentially similar to using Servo to deserialize JSON into Rust. It's pretty much the same. You take a language, in this case it's a key value language with a bunch of features like inline shaders and inheritance, and then you just apply it to Rust. It's just a deserializer. It's not much more complicated than that. It's not a scripting language with an interpreter. It is literally a deserializer, and that's also what keeps it so simple. You can change the DSL and then just reapply it to a Rust object, and you update the state. In this case, we make a desktop window widget, and then I make a slides view widget with a bunch of slides in there. These are the slides. And then what you can do is inside a slide, you can just dump a bunch of UI. Like in this case, we dump the Mandelbrot widget, the numbers, or in this case, the synthesizer app is actually the root of this whole tree, meaning that because it has a fairly complicated piece of orchestration I'll show in a second, I just jammed a slide viewer in the root of my application. And here you spawn the desktop UI, the mobile UI. You can override some values here, like set the width. And so yeah, that's how it's composable. Let's see if I can show you the desktop app. See, code folding is very useful. Frame is like my div. And you can inherit all these components from frame and then start overriding properties and putting in subnodes. It's very similar to HTML, except HTML missed this concept of inheritance. And I think that is essential to UI, because if you look at what this does, is it maps very closely to how UI designers make UIs in Figma. It is very similar. You make an instance of a design, you can override some properties, and that's it. So here's the main application at the bottom, app desktop. And you show the presets widget, then you make another frame, you make a gradient, you have scrollable containers. It is really a DSL, except that it's very easily extendable from Rust. Because that is the important part for a Rust UI framework. How easy is it to use from Rust, right? Because there's always been this fight between how do you make a UI that is designable and how do you make a UI that's programmable? And nobody has really solved that well, because the UIs that are nicely programmable always kind of run out at the end like, okay, well, visual designer, yeah, we tried, we couldn't really do it. Or it becomes this hellhole of CSS hacks just to even attempt it. Let's see, so data binding I'll talk about in a sec. I think what is important to see in the architecture is that we use a poll architecture. So if you have a button with an on-click handler, you can write it in a couple of ways. One of the ways is you write it using a closure on-click. Except in Rust, when you do a closure, you have to put your state into an RC ref cell or something that you can reach, which makes it extremely inconvenient when you have to do that. And so what we try to do is to make an event flow that is query-based but never actually opens a closure and keeps everything unlocked in the flow. So here I hope I can explain this clearly. So the system sends an event to the UI which is like, hey, draw yourself, yes? No, not really. I mean, I could try. Hold on. No, I broke that in my old version. This thing is 4 years old. It's terrible. I have to actually recompile my IDE to do this. Luckily, that's not really a big issue. I had it, but then I lost it. Is that better? It's so great when you can recompile your IDE, by the way. It's lovely. So we get a draw event. And then what happens is you call on this UI object, that's the root node of your UI, draw yourself, right? Draw widget. And what I did is I made the draw flow return a result as a continuation. And that means that if you call this function again after you did that, after you get a result of continuing, then the whole code flow resumes exactly where it was. And this is not a difficult thing. You just have to write your code flow with state machines to be resumable. And you only need to do that in widgets that can contain other widgets. In this case, I'm trying to draw the items in this thing. Hold on. I'm trying to draw the items in this list. Right? So if you make a widget, who owns the data? And this is a difficult question, because if you have a widget that has its own items in there, you often have to give it your data or synchronize your data. This is the way old UI systems used to do that until the functional flow systems started to say, well, why don't you just regenerate the UI when you change the data, and then we'll figure it out from there. And that's exactly what this is doing. You query, in this case, it's a swipe list, and you call the multi-getter, which is a set. So you call get swipe list set. This means that you get any number of preset lists here. That's because this UI can be instanced many, many times, and you don't want to duplicate this piece of code for every instance of the UI. As you saw, you have the mobile UI, multiple instances in different slides. And then you compare it to, if the hook item or the next item is in this set of swipe lists, and if so, you borrow it, and then you draw the items in an immediate mode. Here you see that I get an entry, You have to come up with an ID. This is very similar to React. I just decided not to bother with solving it in any different way because there are not many solutions. Just make an ID. And then you spawn an entry item and you use the convenience APIs to override the text label. This is very different from the template approach where you would kind of inline code into a UI structure. I'm really opposed to that because I don't know how to make a design tool work with that, because as soon as you spread code throughout your design, the design tool doesn't know what to do anymore. So that's why we're very strict about that. And that's it. This is, I think, not more complicated than eGUI, or not much more, but it is way more efficient. So the UI is pretty much entirely incremental, except for my slide viewer where I needed to implement some windowing. It's entirely incremental, so it scales much further than a pure immediate mode GUI where you draw and handle events at the same time. In Makepad, drawing is a special event and everything else is on-click, mouse move, those kinds of things. So how do you handle events, right? This is the drawing part, that's all right. So how do you handle events? Let's see if I can get an on-click here. It's always the nice. Right, so here's the panic button, which stops the synthesizer. It's a required feature in the synthesizer when some node hangs or whatever. And what you do is you get the button set, which is any number of panic buttons. They could be any number. And then you call the clicked method on it with the actions object, which contains all the events that hit a widget. And this query is extremely cheap because it caches the query result of the buttons, and then it just checks an enum to see if there is an event for the particular widget. So this is completely borrow checker unlocked. This is just an if. It doesn't do anything with your state. If you do this as a closure, as I said, you have many problems. And I think this is a really solid improvement. Also, all of these getters return a wrapped component object that is an RC ref cell to a DIN trait. And that means you can keep these things around because the only time they get borrowed is when you call a method on it. And they can also be null. This function actually fails silently, which is, for this kind of stuff, great, because if I remove this button in the UI designer, you don't want your Rust code to crash, right? You don't want it to randomly crash when it does that. You can turn on warnings when it doesn't find it, but you don't want it to crash. So this is essentially a very rugged piece of Rust code that is using convenience wrappers around the components. And I think this is a good path here, because I think the orchestration code for the entire synthesizer, oh, my font is now so big I can't read my line numbers. It's like 400 lines of code. It's really not that much. And so here we have the immediate mode flow, right? Here you have your data that just defines the UI, and as the data changes, you just redraw the UI and you're done. But there are also other paradigms, like data binding, for instance. Here is, if you look at the if you look at all these little sliders, right? This is changing a value in the synthesizer. The synthesizer is running in another thread. It has atomics on all its fields, and you can if you can just bind the slider straight to a value in the synthesizer, you don't need to deal with any event handling. So what I did is I made a data binding system that allows you to bind a Rust struct, because these live things, they're essentially a form of reflection, right? I said that I could apply the DSL to this application using this trait. But that also means that I could implement data binding that way by generating a bit of dynamic UI structure and then applying that to the UI. And that's essentially what's happening here. The slider generates a little fragment of that UI DSL and then applies that to the UI, and then you have data binding. Here's the apply code. Let's see. Right, so this slider is moving that value in the graph, and you use data binding. And that means that the only place where that is stated is here. Right? Imagine how much more work it would be if you have to do event handlers and tying that together. So that's another, and I think it's a different model that that works for. It's a different model that works for different use cases. Okay, how much time do I have? Lots. Okay. All right. Yeah. So the future of this is that we're going to release 0.4.0 soon. That includes all of the platforms. We've written native backends for Windows with DirectX, Linux, OpenGL right now, Mac with Metal, web with WebGL right now, WebGPU we'll add later, and we have it running on Android. And for that I wanted to do a little live compile demo. So one of the things we did with Android was, so we made a new build tool, because Makepad is going to have to build on all of these platforms, right? Like, especially WebAssembly and Android are very specific in the build tooling. So hopefully, this is in someday this will be able to be built into Cargo in some sense, because I don't think these are strange build targets. But they need to do a lot more than just generate a binary. They need to generate a package, or they need to strip a WASM build. So what we did is we made the entire Android SDK installable in one go. I'm not going to do that now, because you'll have to believe me, but you can run Android toolchain install, and it will pull all the dependencies from the original Google sources, strip them all out, and turn it into, I think, 150 megabytes of tooling. That's all you need to build an Android application. And all you need to do then is you do Cargo Makepad Android, which is our Cargo plugin, and the rest of it is a normal Cargo command line. In this case, run and then a project Makepad example Ironfish, which is the slide right now. Hold on, I'm going to do a Cargo clean. I love doing Cargo cleans, but and I'm going to build it. So here's the Android phone. This is a clean build of all our libraries. As you see, we don't like dependencies that we didn't make. So here we have the slides on the Android phone. So that's a solid, what is it, 9.25 seconds to. And I'll make sure that it also plays a sound. Hold on, let me. So this is a little silly trick for me to avoid putting it in a comment block. Let's see, desktop. So you have two types of properties in our DSL. One are user-named objects, which could be child components, and the other one are Rust fields. And Rust fields use a colon, and the other one use an equal sign. So that's an iteration cycle of 3 seconds, I think. That's not so bad. So we have the same synthesizer natively now on a phone. I also tried to build it for web, this whole thing, but this was a little bit of, this presentation was a little bit of, oh wait, now it's a synthesizer. Let me get my presentation back. By the way, this is my workflow, because I compile on keydown with my IDE, and this is also, so when you make an error in the code, it immediately shows you, hold on. Where are my nice error underlined? Guess change, oh, I know. It's now behind the font, see? So let's see. Did I get my presentation back? Yeah. So Rust is so reliable. It's great. You know, you can just do this, recompile, and do stuff, and it doesn't bother me anymore. It just always works pretty much. Let's see. Yeah, so I tried to build this presentation for web, but because I just cloned this UI so many times, WebAssembly actually ran out of memory, and it does that very quickly actually if you do it, if you use, because every one of these things is I think a frame buffer, because I turned on frame buffer caching, so that allocates quite a lot of RAM. And on native, it's just like, I don't even notice. I didn't even notice there was a problem, but on web it immediately starts keeling over, and that is. I'd say that is a very strong advantage of Rust. That once you make a workload that is too complicated for a browser, for a WebAssembly, or needs too much compute, needs too much threads, or having the option to drop to native is something that I've always missed as a web developer, right? So this is also why I'm really not a fan of things like Electron, because Electron is like the same shitty shit as web, except now native, which, like, why? It's like the worst of both worlds, right? So to me, that is the main value of Rust, is that we can now access all these targets, but you can actually use the compute in the target available to you. Let's see. I didn't actually time this talk very well, as you can tell. I need to.
So Rik, you can actually show the synthesizer alone on that, right? You could just show the synthesizer alone on that. That works fine.
Oh right, that was also in my demo. It's localhost. Oh, and I just cargo cleaned it. Oops. So I'll rebuild it quickly. So yeah, this is our work in progress. I still have to write the WebAssembly build tool. As you can see, when you do WebAssembly with threads, you have to compile the Rust standard library yourself. This is a command line flag for the compiler. So now I have 70 dependencies, which is really terrible for me. But it's not so bad. 15 seconds for a build. It's not so bad. There we go. But here we go. Oh, the frame rate is not. You cannot even see this on a projector, but here it looks crap. But see, it should be slower. Yeah, this is slower. But hey, it still works, right? It's like, come on, thing. My click area gone? Well, that's good about browsers. You can refresh them. That is definitely a good thing, because in a browser, refreshing is often used to sort of clear your crappy programming skills of state, right? Which is, but yeah, I think this also works. So this is using WebAssembly threads, and that's a really cool feature that you can use normal Rust threads directly in WebAssembly. I did a whole bunch of code for that. Oh yeah, this is also great. Like, look at that sluggish resize. Oh my god. Like, oh. As a programmer, this hurts me. This hurts me. This hurts me. So then you have this, and you're like, yeah, that's how you do it. You know, it's little things that made me hate the browser. But we're still going to run in it, and that'll be fine. But you can see, oh, I actually. Last time I tried this was much worse, but yeah, it's actually did compile. And this is also where our dependency management is important, because if you try to deploy as WebAssembly in a browser, you don't want to be 10 megabytes of binary, right? Web browsers, you want to stay like, I don't know, 500 kilobytes of a WebAssembly file. I think this one broadly zipped with everything in it. Well, broadly is not zipped, broadly compressed. We will see, I think, around 500K over the wire for this whole thing. So that's really not bad. Let's see if I can show something else. Yeah, this was so this was my first IDE in Rust. I still like it. It's also great that it runs on web. And so the live coding part, this editor part is what we're rewriting now. But this was an early prototype of how it worked. So here you see code variables, and it uses the reflection of the DSL language that we had, which is then called live body. It was different and it was much worse. But let's see, you can use these sliders to slide these values, which is modifying values in a shader right now. So it's hot patching these values in a shader. This tree is actually 3D, sort of. And if you have a quest, you can press the goggles button and walk around the tree with the whole IDE on your hand. This is, I wanted to try to see how fast you can make a UI framework to integrate it in AR and VR environments. And it works very well because, as I said, even fairly complicated UIs like this only take milliseconds to render. If you want to run 120 Hertz, you only have 8 milliseconds. And so that it means for an average UI, like the synthesizer, we spend about 0.5 milliseconds to update the UI for everything you want. And that means you can change your mode of programming to be much more sloppy in that sense. You don't need to do everything incremental. You of course should, because battery use is a thing, but you don't need to. You don't need to anymore. Let's see. Let's see if I can show anything else. Okay, the file tree is now really, really tiny. Let's show the numbers. Yeah, let's show the piano widget. Audio graph. Piano. Yeah. So I'll show a little bit the shader programming that you need to do to draw that piano. Because to me, it's these kind of widgets that are that really benefit from having shader styling, right? If you just change the background color, you can do that with any UI system. But if you want to draw these kinds of piano keys, you want to write a little pixel shader. So in Makepad, you can draw a shader by just defining some functions that look a lot like Rust, but they're kind of not. They're semantically closer to GLSL because I have to transpile them to all these backend GPU languages. So you define a pixel function, and self, in this case, is the data I/O, or the data in from the Rust side, where you set values and you can read them directly in the shader. So for instance, in this case, you have an, here, let's see where the piano widget is, piano key, yeah. 5 minutes, okay. Good, yeah, this is good. I can explain a little bit about the shaders. So you make a struct in Rust. You derive live on it. This is the binding mapping. And as you can see, I also have an attribute called dref to do inheritance, which I know is an anti-pattern, but I don't care. It works very well for this feature. You derive the shader from drawQuad, which draws a quad on the screen, and you add some properties, like is black, pressed, hovered, focused. And then in the shader, when you inherit the object from that Rust type, you now have access to self.isBlack. So this compiles away the entire barrier between the GPU and the CPU, and that makes it much more ergonomic to do shader styling, because otherwise you'd have to, cram values in an attribute array and calculate offsets by hand. This is what compilers are supposed to do. So it's one of those things where having our own shader compiler is very convenient. And in this case, we draw an SDF shape. So this is a very funky API. It's essentially a canvas API in a pixel shader. You can do circle, circle, combine, union, all these things in a pixel shader. And what is cool about a pixel shader is, like, you can set the color of everything per pixel. So in this case, I'm drawing a box. This is a rounded corner box. And I'm using as the color a function, in this case, black key and white key. And black key is this little height map. It's like a little height map where you do a dot product and then you have a light. And the white key is simply a gradient. So here you see how in a shader you can compose different rendering essentially by just overriding a color. It is a very different experience if you can override a color per pixel than if you have to do it with the vector API, because all the browser UIs or most UI kits are essentially based on vector APIs. Let me see if I can find a little example of how you then style it. Here I use a distance field to draw a little shape, right? This is probably an icon. Let's see what this is. Oh, it's a drop down. And the same goes for text. So here you have the get color function of text. Because the shaders are inheritable, I can override methods that are called in the base class. So you can override get color. Because pixel in the text render is a bit complicated. It does a bunch of texture lookups and color space mappings. But here, you can still return a color per pixel. So this is a text renderer where you can define the color per pixel for anything and parameterize it directly from Rust. And this inheritance structure, I think I have never seen before, where you can inherit shaders to do your UI styling. And I hope it catches on, because for us, our designer, Sebastian, has actually made this entire UI, including the pixel shaders, which I find very amazing, because he's not a programmer, he's a designer. But apparently it is convenient enough that, that you can write these things. So I have 2 minutes left. Does that include questions?
No.
No. Okay. Yeah, let's do that. I think so. This was I was skimming over the surface here because the surface area is very, very large for this project. We have written every single component from our own implementation, micro implementation of Servo to Eddie's popular things like your own regex engine and a WASM engine. So that we're going to merge that in soon. And of course, the reason for that is that we want to minimize compile times, because the way we think Makepad will happen is that it'll become the foundation library or a foundation library to build applications. And that means that every single hello world button click thing will include our library dependencies. And right now, on my fastest Linux box, with everything cargo cleaned, I can do a clean build in 5 seconds for this entire stack. This whole synthesizer will build in 5 seconds. And I believe that with that focus on that compile time, we can sort of make things lightweight again. Rust is not known for its lightweightness, or especially not with a lot of dependencies. And if you go to UI, you very quickly hit the 400 or so dependency range. And I don't find that a very pleasant experience if I accidentally type cargo clean or have to have a new Rust nightly. And also not CI. CI is going to clog you every single time. You have to wait for half an hour because these are usually very small 2-core machines. So yeah, we err on the side of not invented here. It also makes it fun to do because we get to build lots of stuff. But otherwise, that also means that what I could talk about here is extremely wide in terms of concepts. Yeah, I think I'm done.
Oh, thank you very much, Rik. Well, we got time for questions, and we got one of these. We got a catch box, so there we go.
What is the current state of accessibility support, thinking screen readers?
So I'm of two minds here. First of all, accessibility is an extremely complicated problem because of, if you look at the specification, there's like more classifications of objects than I can even remember. And I have the feeling that by the time I'm done implementing half of it, AI is going to be the screen reader. it is a little bit, yeah, we can completely do it. It's a tree, memory. I can make an accessor for it, or I can spawn a shadow DOM. I haven't done that yet, but yeah, I have this feeling that by the time it might be important, you can just ask an AI to do it for you. It could be that it's computationally too expensive, right? Because you're going to need to run a pretty hefty GPU full blast probably to assist you. So there's that consideration, but it's definitely possible. I just haven't worked on that yet, except for reading specs and trying to get a handle on what to do.
Excellent. Oh God, more questions. Okay, we're gonna do 3 questions. So the 3 people that raised their hand, we're gonna do those, because otherwise we're gonna totally run out of time. Now I'm gonna throw this thing, which is gonna be totally awful. I can't believe it.
What about iOS?
iOS. Well, I wrote this. This thing is running on Metal on all of the native Apple APIs directly. So I kind of prepared iOS. iOS should really only be a little bit of NS something or other implementations, because I looked at how it's implemented for some other abstractions, and yeah, it's not hard. But the Android stack was definitely a lot more work because we had to get on there. We have support for Apple, and under Linux we have Android. We also have direct rendering. I wanted to run it on a Raspberry Pi full screen to see how many frames per second I got, and I only got it to like 30, and when you only moved your mouse you could get 60. The Raspberry Pi is a really dreadful device to feel good about rendering about, because if you clear the screen twice you run out of memory bandwidth.
In short, we're going to support it.
It runs on the Raspberry Pi in full screen in direct rendering. And X11, we don't have Wayland right now, web, and Windows. Oh yeah, I also wrote a Windows RS stripping tool because it's 3 million lines of Rust, which is not in line with my compile times. But if you strip it, I think the whole dependency stack for Makepad is only 20,000 lines of that library. So.
Can you pass the mic back there? Just throw it to the back row and then pass it further up until we're... Or do it in one go. Oh, nice. Woo!
So I was curious about the Android.
Yeah, you have to talk into the thing, yeah.
Does this work? Ah, nice. I was curious about the Android tool you were talking about, where you like strip out the SDK.
Yeah.
Is this like, can you use it with different tools? I use Cargo APK, and I hate having this big Android SDK on my computer.
So it is a very dumb thing. It's essentially a shell script that I turned into Rust to download and strip hold on, tools, cargo, source, Android, SDK. So essentially, it's just all the paths for all the different platforms to the Android tools, and then it's a bunch of unzipping. And I have here, yeah, this is the list of files. So I binary intersected the SDK. So I essentially deleted half of the SDK and tried to compile my Android app until it stopped working, and then put it back and just split the other half. And if you do that, actually, you're only left with a few files, I think 38 in total, that you need to extract from the SDK and put in a directory. And then you can just call it, like, let's see here, compile, where you do, come on.
If your question is actually how do I build my Rust application, just shell command, stop to me later.
Yeah,
Nice.
so this is this script is designed to compile the Makepad application, including the resources, and contain them in the APK. If you're just doing a DLL, you can just steal the few build commands that are in here to do it.
Awesome.
All
Thank
right.
you.
So the next question was next to you, right? Yeah, awesome. So that is the last question. Thank you.
How's support for drag and dropping between Windows and clipboard?
Well, that guy started on it and never finished it. He has other stuff to do.
It's not finished yet.
This is also where open source is nice, right? Like the code base is really not that daunting. I think it is. First of all, it's Rust, so that means that it is not nearly as scary as someone's dialect of C++. And also there's a lot of platforms. So we are open for assistance in these kinds of areas where you're like, okay, I'll implement drag and drop for Windows or for X11. X11 is the party. That is really fun system to build. Oh my. Yeah, it's like archaeology into.
All right. Thank you very much, and give a big round of applause for Rik Arends.
That was a rock star moment.
Just hang on. These are the technical sort of things that are going on in between. You got it? Yeah. That looks nice. Let's see. Slideshow. All right. Can you switch it to my laptop? Yeah. So I heard through the grapevine that 4G and or 5G, depending on which provider you have, is dreadful. If you want to use the Wi-Fi, grab your phone now, take a picture of the slide, and use that as the login credentials. I'll give you a couple of seconds to take a picture.
Hey. Is it Congress with 2 S's or just 1?
Yes. Oh God. It's a Congress with 1 S.
All right, thanks.
Oh, is it for you? See? Yeah, it is actually 2022. And I think autocorrect turned it into Congress with 2 S's. I'm very sorry about that. And with that, so everybody get it? It's Congress, 1 S, last year. Excellent. There we go. Quick test.
I think you turn it off.
You have to be kidding me. No.
That's fine.
I'm very sorry. So, our next speaker is Martin Hoffmann. He's a colleague of mine, so doing this intro is super easy. He's the person responsible for getting us into Rust in the first place. We had a little shootout between Rust and Go to see if what would be a better fit for us. Being a classic C shop, we've been around since 1999, and then 5 years ago we started a brand new project. We were like, okay, are we going to do this in C? Or maybe there's a better language? And then we looked at some options, and the Rust versus Go shootout lasted for all of, what, 2 hours?
Yeah.
It was pretty much settled that Rust was for us. Martin got, well, I think half the Anonymous Labs crew into Rust now. We're slowly transitioning everything that we're doing to Rust, which is actually kind of cool. And Martin likes to be ahead of the pack. So he was exploring pins, which is kind of a mystery to you all. In his spare time, Martin likes to be on trains, and when he's at home, he likes to do maps of trains, of railways. And with that, it's going to be very exciting, I think. Take it away.
Well, let's find out if it's going to be exciting. See if this works. No, still doesn't. All right. Yes. So, start here. I have a background in network development, so server software and that sort of stuff. So whenever it was, futures started to
come around and made network development, the whole select and poll stuff, much easier. I obviously was very excited. And looking at the definition of a future, it's all very obvious and trivial. There's a poll function that you call and keep calling, or someone keeps calling. I don't need to care about that, until there's a result. But then this happened. And I was, what? I should probably look into this, because also what happens is this then trickles through into other things. This is the read trait from Tokyo, and you see self also is this mysterious pin thing. Now this was in 2018, so that's 5 years ago. I still haven't looked into it. And I figured I'd trick myself into doing this by proposing a talk. And apparently the program committee also hadn't looked into it and thought, yes, let's do that. So what are these mysterious pin things? We need to start by talking about move by, what I call memcopy. That's not the official term. I made that up, well, yesterday. And this is the idea that the Rust compiler is allowed to move things around in memory as much as it wants to, and that all the types can be copied. That is, you can just take their bits and move them from here to there, and they're still valid values. Right? Well, that's trivial for something like a usize. A 12 is a 12, no matter where it lives. It's also true for more complicated things, like this thing here, which has an array and a usize. You can still just take it, move it, it's fine. It's also true for really complicated things. There's like complicated types in there. TCP stream probably is not trivial. There's an arc in there as well. So, but still, the rule is you can move it from wherever it lived to somewhere else, and it's still fine. Side note, this is where copy comes from, sort of, because the difference between moving and copying is really just that in the move scenario, which is what we call the move semantics, wherever it used to live can't be used anymore, whereas if a type is copy, you can still use it. So move semantics, which you've all heard of, because the compiler told you about it, means that you create a value, and then you can move it somewhere else. So in this case here, we're creating a stream, which technically is created inside this TCP stream connect function, and then moved to us. So that's already a move. We do the same with the metrics, which uses the default trait, which also, again, creates a value inside the trait method and moves it out. And then we're moving the whole thing into this TCP or TLS stream enum thing. And again, we're moving it around. So we can do even more fancy things. We can move it from the stack, because that's what we did with all these let things. We can move it onto the heap. Again, it's just a move. We take it from the stack and move it to somewhere in the heap. And then we can take that pointer that we just made, because an arg is a pointer really, and move that. Now here's an important thing. Once we move this on the heap, and we're moving the pointer, we're not actually moving the object anymore, or the value. That stays where it is, right? So in this case here, we're making an arg, which is a pointer and a number, and we're pushing it onto the end of a vector. Now we're only moving that arg, but the TCP or TLS thing stays where it is. That's important, because we'll use that later. But you can still, if you have a pointer on a heap, or wherever, because you can also obviously have a pointer to something on the stack, you can still move it. You just have to be a bit sneaky about it. And this is what core or std mem has this function here, swap, which basically takes two mutable pointers and just exchanges whatever is there. And as you can see here, it actually does exactly a move. It copies the bits, right? So pointer read reads whatever is behind the pointer into this A, from X to A, and then we later write it back to B. So again, this is a move. So crucially, we can move things by memcopy if we have an unadulterated own T, so not a T that has been stuck into a pointer, but an actual T, or we have a mutable reference to it. And why is this important? Because this whole thing is the reason why we can use the stack so much in Rust, right? In C or in Java and things, what always happens is you make a value, you move it into an allocated bit on the heap. We only need to do that on Rust, and the reason we can do that, we can get away with it, is this move by mem copy. So this is really great, except there's always something. And in this case, it's something called self-referential struct, right? So here's a trivial example. We have a buffer, which is just an array of bytes. And we want to keep track of, like we want to read into that buffer, and we want to keep track of what part of it we have filled. So we just do a U8 slice. And that slice is supposed to point into that buffer, right? So it looks like this. The buffer, and then filled has, it's a slice, so it has 2 pointers, one where it starts and the length of it. Now, if we move this thing, we move the actual bits, which means that slice there, which is just 2 pointers, points to where it used to point. That doesn't get updated because you just copy bits, right? So that's going to be bad. And this is why you can't actually do that. This is one of the features of the whole lifetime thing. Well, you can do it, but then you have to do unsafe code, and then you're on your own. So let's say we don't actually need that, but there's another use case that actually needs this, which is async functions and blocks. Because what they do is, this isn't coroutines or threads or anything, right? So they don't have their own stack and it's all expensive. What actually happens is the compiler sort of desugars this into a state machine, which is a sort of an enum. And every time you call await, it generates a state for that, and with that state, it keeps all the variables and the things that it needs later. Right, so in this case, the first state is before we actually start, because if you call an async function, it doesn't do anything, it just gives you this future thing back, which is that thing here. So the start basically needs to keep all your arguments. And then when we call the, and then what we're doing here is we're basically just taking this, this bytes vector and split it into 2 bits, which both of those are references. And then we're just using them across await points here, right? So for the first await point, we need to remember for later the actual vector, because we need that at the bottom. There's a send message at the bottom. And we need write. Now, write is a reference into that message, which also lives inside of that enum. So we've made a self-referential, well, structure enum. So that's kind of bad. So how do we fix this? Well, so what we said is we can't do this because we can't, but if we move around the enum here, which will happen, right? Your runtime will just put it here and put it there and do stuff with it. But we can't move it. So we just need to make sure you can't move it. And that's exactly what the pin does. This pin is just the thing that makes it impossible to move the struct around. And so you can have it be self-referential. Again, the main usage, and this is also why this happened to appear in future here, is for async functions. That's why we need it, so that you can make async functions. So that's why it appeared there. Now, how does it actually do that? First, the important thing here is that pins are for pointers. So you always pin pointers. You never pin values. Like a pin U32 isn't a thing. You always pin pointers. So like references are pointers, mutable references are pointers, but also things like boxes and arcs and RCs and whatnot. And if you make your own pointer type, then that might also be pinned, right? So you could have a complex struct that contains pointers, then that could also, no, hang on, that's not true. But you can make a smart pointer that has things, and then that might also be pinned. Why does that work? Well, so we said that there's 2 ways you can move things, or move by memcopy, as I called it, things. One is you need just an own T. Well, we don't have that, because the T has been moved into the pointer into the pin. So we can't get to that, so that can't move. But we also cannot call, we cannot get a mutable pointer or a mutable reference to that value, because the pin just doesn't let you do this, right? If you write your type, you decide what you do. And the pin just doesn't allow you to do that, which means by just being this little thing, without any magic or anything, it just stopped it from being possible to move that struct around. That's all the pin does, really. Except, hang on, if you look at the pin, there's this. So it implements deref mut, which I just said it doesn't. Well, that's just weird. But I wasn't lying, I was just not telling you the whole story, which is this. It actually only implements this when the target type, so that's our T, for the pointer is something called unpin. Great, now what's that? Unpin is a trait, obviously, because it's a trait bound. And crucial here, because that leads to confusion, unpin is implemented by the type your pointer points to, not by the pointer. The pointer doesn't care, the type it points to needs to be unpin or not, right? And what it says is, actually, just move me around, it's fine. Because most types, as we've seen, can be moved just fine. I mean, that's a fundamental principle of Rust, that you can do that. So most types actually can be moved around, and we don't really need this pin thing, we just need this for these weird self-referential things. So, unpin is in fact an auto trait, which means the compiler implements it automatically for all types that it thinks are unpin. That's the same way that sync and send work. And the way this works is that basically everything is unpin. All the built-in types, like your usize, obviously, you can just move a usize around. All of these are unpin. Complex types are unpin, so structs and enums, if everything inside of them is unpin. That's the same as for sentencing. So really, everything is unpinned, then why are we doing this? Well, there's a thing called phantom pinned, which is one of these marker traits, like phantom, phantom data, whatever it was called, which is not unpin. And this is really weird, so it's not unpin, but you know. So if you want to build a self-referential struct, then what you do is you just make phantom pinned part of your struct, and then magically it's not unpinned anymore, which means it cannot be moved around. Oh, hang on. No, how do you get back? There we go. So, in summary, pointer types can be pinned by sticking them inside a pin struct. This pinning blocks the move by memcopy by blocking access to representations of the value or pointers to value that would make it possible to move them. But it only does that if the type itself shouldn't be moved. Otherwise, it just basically does nothing. And because the latter, you can just move stuff around, is almost always true, you don't actually need to care about this, which also means you cannot read up on it for 5 years. But now, we still have to implement futures, maybe. So we still have to do these. We still have these pins and things, and we need to deal with them. Now, let's say we want to wrap a TCP stream, and we want to add some metrics to it, because that's always coming up, and it's always annoying, but we need to do it. So we make a struct that contains the TCP stream. It contains a TCP metrics, which for the rest of this we don't actually care about. And we need to implement async read, async write. Let's just look at read. So there's the method that we had before. And now we get the self as this pinned pointer. And all the rest is just not important, because what we really want to do is we want to call Paul read on the stream member of the struct. That's it, right? Now, how do we do this? Well, let's go and have a look at TCP stream in the documentation, and hooray, it implements unpin. So actually, we don't need to care about all of this, which means the pin implements deref mut for the pin TCP stream, which means we can just do this. We can just take a mutable reference to the member. It just works, because deref magic and things. So now we have a mutable pointer or reference to stream. And now we need to just call Paul read of it, except we don't read the mutable reference to the stream. We need the pin of that. Now let's have a look at the pin documentation. And there's an actual pin, there's an actual new function, which isn't even unsafe or anything. You can just use it. But if you look at the trait bound for the impl block, it requires target to be unpin, which we are. So I guess we can just do this then. And we can. So that just works. Which then you can turn into just one line, and you're done. It's also important to point out here that pin is one of these transparent structs, which basically means all of this, what we're doing here, all the pin new and the this and the that, it all goes away. The compiler just compiles it away. So it's really just a call on poll read on that inner thing. Well, that's nifty. So what was all the fuss about then? Let's make this generic. Right? So we want a metric stream for not just TCP stream, but for anything, because we're doing TLS, obviously. Now, we only need T to be async read for implementing async read, obviously. But just do the same thing, see what happens. Well, obviously, this happens. And the compiler rightfully tells us that our T isn't unpin. The story goes a bit further, because also, obviously, if T isn't unpin, you also can't do the mud self stream thing there. So that doesn't work. We need to do something else. And what we need to do is something called pin projection. And, well, this is Rust, so we not do it ourselves. We just go to crates.io and search for something. And there's two crates here, pin project and pin project lite. The difference between the two of them is basically pin project can do more things, and like weird sort of side effecty things that we don't really have time for now and also haven't read up on. So basically always you want to use pin project lite, and like if you use something like Tokyo, you have that anyway because Tokyo's using it. So just use it, doesn't even change your dependency count. So what does that do? It gives us a macro called pin project, and we just wrap our struct definition inside that macro, and we mark the members of that struct that we want to have pinned references for later down with this attribute pin. Now what this macro does under the hood is it creates a like a little shadow structure that looks exactly the same, but for each of those things that we marked with pin, it actually has a pinned thingy thing. So what you can now do is, you see this down in the implementation block, you just call project on self, which is a function that the pin project also gives you. And this then gives you a struct back, this sort of shadow struct that we got, which consists of a pinned mutual reference to mutable reference, I'll get this eventually, to the pinned members and just a regular mutable reference to all the rest. So we can just call stream on this, which gives us a pinned mod self, and we're good. We can just call that. And that essentially is it. Again, if you're doing unsafe things, then you're on your own. You need to read things and whatnot, and I guess have lots of seg faults. There's one thing I want to say in the end, which is what happens in the end, which is if you want to implement drop on your metric stream thing. Now, what happens if you do this, you get an error saying that there's a conflicting implementation. And what pin project basically does is it prohibits you from implementing drop, because implementing drop on a pinnable struct is dangerous, because in drop you get this mud self, so this mutable reference, but this self may actually be pinned at this point, right? So it may actually be that you couldn't move it, you shouldn't move it, but the compiler gives you the sort of tools to actually move stuff, because you can, as we saw with swap, you can move things around. So the easiest way is to just not be allowed to implement drop. And if you actually sort of have to walk around this, if you need drop, then you need to be very careful to not actually move things in your drop implementation, which, this being Rust, makes it a little tricky. So just remember, don't do drop. And that really already is it.
Thank you, Martin. And now I'm really curious whether somebody has questions about this, or are you like completely overwhelmed? Oh no, the mic is already in the right place. There we go.
Yeah, I have a question about the drop. So that compiler error seemed like you just cannot implement drop. Is there some way, like an unsafe way or something to implement drop?
So this pin project thing is just basically like it helps you with doing this projection sort of magically, right? You can, of course, do this yourself. So you can implement a function that takes a pinned mod self and turns that into a pinned whatever the T that we had, right? The stream thing. You can do that. That requires unsafe code. And then if you do it that way, then you can do whatever you want. You can implement drop. It's not a problem. It's basically this pin project is just for all the normal cases. You can just get away with doing nothing.
Excellent. There was another question. Oh, God. I'm running away from you. This is great.
Hello. So what I was thinking is that, so most types are unpinned, right? Yeah. But like an async function that's an arbitrary like future that might or might not be so referential depending on the contents of the async function, right? So is then a future that's generated as syntactic sugar from an async function always not unpin?
I think it is never. It's never Jesus Christ. It's never unpin.
Okay.
So I had the same question. I wrote a quick function that didn't do anything.
There's confirmation right there.
And it was still not unpin. So I think all async functions are not unpin.
Okay. Yep.
Excellent. And I saw a question all the way in the front. This is fun. I'm just going to bring it over to you personally. Somebody got hit in the head with this thing already. So there we go.
So you said you waited 5 years to look into this. What documentation or other change in Rust would have made this substantially less intimidating? What could we have done better to make this not as terrible?
I think the main issue is if you look at the module documentation for the pin module in STD, it is obviously complete and accurate, but it sort of starts in the middle, right? I was considering actually thinking about maybe as a consequence of this all, try to write a better sort of introduction to this module and submit that as a PR. We'll see.
Please do. I'd love to review that.
Yeah.
All right. Anyone else have a question? No? Oh, there.
Ha ha.
This is great.
Don't need to go to the gym today.
Mild throwing, there we go.
It's not so much a question, but the crate you just pointed to, pin project, actually has a mechanism to implement pin drop, where you get a drop, where you get a pin mutual reference.
That's yes, but that's probably pin project, not pin project line?
Yeah, that's pin
project. So that's one of the cases where, yes. So that's one of the cases where you want to do that instead of the...
So if you want to have a way to do it without shooting yourself in the foot, use that crate.
I think there's also in the documentation for probably the unpin module, the pin module, there's also, it sort of lines out how you do this by just converting your mutual reference into a pin mutable reference, damn it.
All right. Oh, yeah. Dirk-Jan is setting something up, so that allows me to sneak in another question. There we go.
Thank you. So I feel this is a stupid question, but probably going to be laughed at. But the example where you introduced the pin crate, I was wondering, couldn't you just use a trade bound for unpin on the implementation?
Yeah. Yes, I forgot to mention that. Yeah, you could do that, but obviously, why would you if you can do this properly? Yeah. I think in practice, for this particular example, you probably could just get away with it because all the stream things are probably unpinned because there's really a reason why it wouldn't be. Because I mean, ultimately, it's just a file descriptor, right? It's just an integer. Yeah, well, I needed an example.
All right, and thank you very much, Martin. Now, before you all run out and for the coffee break, first of all, Mara Bos wrote Rust Atomics and Locks. She's here to sign the copy of the book that you brought, but we're also giving away some of the books. And all of you have a number on your badge. And with that number, Dirk-Jan is going to do something special. There we go.
So I wrote this little random number generator. You can inspect it here so you know it's fair. And then we hope we can trust the laptop and the OS and stuff. So apparently there should be about 275 people who have a number. So let's see if that works. So here, if you have one of these numbers, please in the break that's starting now, go down to forum and come to Mara's table and get your book. Yeah, and I'd like to ask everyone to be back in your seat around 11:40, so we can start at 11:45. And also, there's a pretty full house. There's a bunch of people sitting on the stairs right now. So please, when you find your place after their break, try to, I think they like to call it defragmentation. So you know what that does, right? You used the Windows PC 20 years ago.
Can you make the font a little bigger? People in the back can't read the number and they don't know whether they won or not.
I should be able to do that.
Yeah? I don't, yeah. Recompiling the terminal. There we go.
That was a little easier than the way Rik did it. Yeah, so let's go for a break, go out and have some food and drink, and see you all in 20 minutes.
te big.
Can you give me around 18 minutes or 20 minutes for 5 minutes, because I'll have 5 minutes for talk in the last end or not?
Yeah, I'll give you a 5-minute sign. Is that okay?
Or give me 10 minutes time.
Okay, I'll give you 10 minutes time.
Because then I can stop a little bit earlier and take more questions.
Okay.
I want to take questions rather than me randomly
Yeah.
things.
Okay. 10 minutes for questions. You got a half-hour slot, so 20 minutes for your talk?
Yes.
Okay,
I mean,
20 minutes.
after 20 minutes, you can tell me, like, I can still demo. I have demos.
Yeah.
So I can demo, but I want to do, like, talk,
Then you know where you are.
Yeah.
Excellent. I'll take care of it.
Should I, someone put
No, you can. Make it 10 minutes. Yeah, so, no. You take it out.
That's my Wi-Fi. I still can't get in.
Oh, yeah, no, so it's on us.
I did that, but it still doesn't work. So, macOS, iOS.
I decided that I had to do it twice.
on my phone, I had to do it for half an hour, then suddenly it connected. On my computer, I couldn't.
I'm 100% sure that these
takes a while.
credentials.
Okay.
And if it doesn't work, just try it again, because I needed 3-4 goes to get it working.
Wil je het straks nog 1 keer oproepen? Dus ik dacht dat ik
Yeah. Ladies and gentlemen, I just want to remind you that there's no eating and drinking in here. So if you still have coffee or something to eat, could you please take it outside? Thank you very much.
I'm not in a hurry at all. I'm just making sure that my slides and all tabs should work.
Yeah, exactly.
I always screw up.
We still have 4 minutes to go. That's all fine. Yeah. So you can get the mic up there. Please go upstairs, and then So this slot will take half an hour. So you got half an hour. Go. I'm really impressed with how orderly you all are. Timely. It's kind of incredible. All right, 34. Okay, last couple of people taking pictures. Very nice. Everybody finding a seat. We want to start in about a minute or so. All right. Let's go for it. So for our next talk, I would like to introduce Kushal Das. Kushal works at the Swedish National Research and Education Network, SUNET. He's a Python core developer and the president of the Python Software Foundation. Or
no,
not?
Director.
No.
Only director.
Oh, director, not the
Yes.
president. See,
Yes.
it says director on my card. I just remember it wrong. And you also participate in the Tor project, right?
Yep.
And contributes to the Fedora project?
Yes, among many other things.
The endless list of things that you contribute to. So, well, about your talk, you're going to use Rust to write Python modules, which should be pretty awesome. I'll stop talking. I'll let you take it away. Thank you.
Thank you. So, also to say, this is my first time in Netherlands. I'm based in Sweden, and I'm here only for the conference and to meet all of you, which is amazing for me. So you heard a little bit about myself. Who am I? But I still want to repeat parts of it, that I work as a public interest technologist at SUNET. SUNET is part of the Swedish government. We brought internet a long time ago in Sweden, like the first ever internet provider. We still provide internet, but we also provide scalable and secure infrastructure to rest of the higher education research institutes and places across the country. So every country has similar networks, like I think it's called SurfNet here, and then we have FUNET, SICT, and other groups. I'm also one of the core person in Tor project. I build and release Tor on rpm.torproject.org. That's part of my work and also part of the community team. I write regularly my blogs in kushaldas.in, and you can find all of my contact details there. And as the last part, I'm also a Python programming language code developer, known as CPython, and director in Python Software Foundation. So that brought me here, like today in a Rust conference. This is my first Rust conference, by the way. So I'm here, but what I'm doing here, why? I'll go back a little bit back in my life, 2009-10, which now seems oddly over 10 years. I was working for Red Hat, a small, tiny open source Linux company, as you know. But I was writing a lot of Python code, like for tooling and services, and then I got hit by something which is pretty common. And this, if I remember correctly, that was a web application, and I was using Django back then. It's not Django's fault, it's my code, I know, but that was performance was an issue. How to retrieve the data fast enough, how to do all the things I need to do, and showcase. Then in the Python documentation, I found this piece of C code, which the actual part of the C extensions documentation. You can search about it. It talks about how can you create an extension in C programming language. That's good. Can I try that? Will the extension compile? Yes, of course. Will it do what I need at that moment, back in 2009 and 10? By the way, as my background, I did computer science engineering as my bachelor's, but I knew I was always a terrible C programmer, and I am. But I somehow managed to write enough code to do the things required at that moment. It had performance. But with the time, while working on that project, I understood like how bad code I have written. As you know, anyone thinking about security or anyone who does enough of testing, you know about different inputs, correct? And how the output should behave. And I learned, luckily not on production, but learned enough number of times while trying to fix my C code. It's like how to get this actually working. Still lucky enough, that was an internal code base, so I didn't have to worry about too many people attacking it with random input. The input was sanitized way before that I had to do at the end. But that was still a big question in my life. It's like how to get it done. Now, after that, again, today, standing here, why am I talking about Python in a Rust conference in front of a group of Rust developers? To start with, you may have heard that Python is slowly becoming, or already became, in major parts, the first language to learn. It's something which helps a lot of people to get things done. Data science is one of such places. The index, like we are there on the top language. I still don't know how this works, but it says like, yeah. I really don't know how it works, but the more I talk, I find more and more new developers. They are picking up Python as the first language, then learning different things in various places. Like this is across the world. So Python is important. At the same time, it's us as developers. I think one of the most important things for us is to get things done in a safe, secure way, and for the perfect use cases. I'll not say business cases. A lot of users are not businesses as such. But the use cases we have to solve someone else's problem. A lot of the times, the problems we are solving are not ours. It's someone else's. So we have to make sure we can provide them with that kind of solution, which works. Now, time passed by. I started doing a lot of different things, still writing majority of things in Python. But that question was up on my brain, like how can I do it better? In between, I found Go also, which was nice. OK, can I use something in Go and write something, use it from Python? Maybe yes, but just after doing one try, it was like, no, I'm not doing it again. I'll write pure Go if I need to. So the question remained in my life. And I'm saying personally from my point of view, every few months or things, let me search if people are doing it in an easier way. I want to do something which not only I can do, but another new developer can come in and try to repeat. So it's not about me. It's more about like we have to build up a community, whatever we are trying to achieve. In between, this thing happened. You know, Rust came in. It came in slow in one way, but it came in fast, like things getting rewritten, things like we can see improvement in various places, etc. I can see on internet. I could go to conferences where I could see like people are talking about Rust among themselves, how they're using it, everything. I opened up the examples, and I'm like, OK, maybe I'll try to get back it later. It looked a little bit difficult for my IQ level at that moment. I'm not saying my IQ increased, but I can read better now. So this is my blog post from 2016. I completely forgot how long ago. So I took the screenshot 2 days ago, I think. And then I realized I first tried to write Rust in 2016. And generally, the way I learn about anything is trying to write a tool or something which I can then use. So if you go to the blog post at the very end, you will find I tried to write something which I can use inside of my MUT, the email client, so that it can help me to find email addresses. I did that with the help of, if I remember correctly, IRC channel from the Rust. I don't even remember the name. I'm in the Discord channels these days. But I somehow managed to do that. And then I didn't write any Rust for next few weeks. Then I tried to come back and realized I can't even read what I wrote. Brain totally destroyed. And I tried and tried. Then I thought, my old question, what if I now try to see that I can write something in Rust and use it in Python? Is there any easy way? I did not search about it at the first place, by the way. I found a project, pio3.rs, where obviously more people than me thought about this, and they are actually better programmers than me. And so and better Rust developers also, and better Python developers. Even though I'm a code developer, I don't know everything about Python. So these people decided, oh, we should fix this problem. And they started writing this project in Rust, along with the tooling required for any normal Python developer to start writing Rust, expose it as an extension module for CPython, and consume from Python. The thing I always wanted. So how that changed the world. So if you ever used Python here, anyone who all used Python, just to see that, raise hands? OK, a lot of you. So you may have heard about this project, tiny little project called cryptography, which almost every one of us are using in some way or other. And then the cryptography authors decided to rewrite the internal parts from C to Rust. There was some excitement, as you can see. This is a screenshot, again, from the GitHub issue. You can go and read the whole thread, how people reacted and what was the issue. But you can read my friend Christian's comment. Not going to happen. Rust dependency will stay to replace C code with an actual safe language. And that happened. And now all the Python users, almost everyone who is using Python, they will be using the cryptography module one way or other, in my guess, most of them. So they are now already consuming something written in Rust. That brings me to a module. So I'm a heavy open PGP user, GPG, PGP. I wanted to always use it more from my code. There is still a Python module available which uses the GPG binary inside and like executes it and tries to do something. And the author got angry and renamed the package as, I don't remember, I think pretty bad privacy or some really strange name because it keeps breaking all the time as GPG updates. So, and I found a project written in Rust called Sequoia, sequoia-pgp.org. It's a great library written from scratch to do open PGP operations in Rust. So I thought, let me try. This is a perfect use case where I have Python. That's my end goal. I have a perfectly written library in Rust. Let me try to start working on it. So in 2019, I started working on the actual library. And while I'll now open up the documentation and things, but while doing that, my Rust skills slowly improved. So for most of you, will find oh, we will write so many Rust projects and learn. But for me, that Rust project was something which I really wanted to use. This is from the documentation. So if you know Python, you can actually read it. It's almost like English in that way. It's like we create a key store, we get a key, we encrypt with some key, and then we try to decrypt with a password. Sorry for the example password, but yeah, that's in the documentation. And we can do other things, like we can actually verify the Tor browser with the latest release and with this module. I'm showing you still Python code, by the way. I'll get into the Rust right away after this. But while maintaining this library for over 2 years, my skills slowly improved. And I hope you remember about my comment is that I thought Rust is difficult. I was still based in India. Then I moved into Sweden. And for the last 2 months, I am actually every day going to the Swedish school, trying to learn Swedish. And I don't know how many of you learned other languages outside maybe your journal or nearby languages. It's extremely difficult. Rust is nowhere near. It's so amazing compiler, tells me everything about the things I need to fix. That's not the case in a real human communication. We know writing API is difficult, and we should really think about us, and that language is the API or the data we are throwing at each other and trying to make sense. English is not my first language. I'm still trying to learn how to speak or write better. But this happened. So yeah, my thing slowly improved. Now, as I said, I will try to do a couple of live demos, part of my talk. A few of them will be code, and then actually why this is going to change the world, how we see it. Cryptography is one example I talked about. So the PyO3 authors, they wrote a tool called Maturing. This helps any new Python developer or any Python developer to start a project in Rust with this command. I'm not going to execute it because after that I just saw like if I try to Maturin build tries to fetch from GitHub and my network doesn't work, so I don't want to do that part. And so this is the structure it creates. It creates all the files required, and it also creates by default something called pyproject.yml, which is about the Pythonic way of building things, and this is where we get all the metadata. So this is the default example. It creates a function and exposes it. We're going to expose this as py function, sum as a string, 2 usages, sum it up, and send it back as string. This string is now going to expose in Python as a Python string. And then finally, in the actual module, I'm just adding the function so that the function is actually exposed towards Python side. By the way, from now on, for the rest of my talk, if you have questions, feel free to ask. So, Maturin developed. So it did not do anything. It's not actually building, but I just wanted to show this is how we build for development purposes. Python, I'll go up, import RustNL, then you can see some as string. Maybe 42. Yes. So this works. Now, if I look back, again, you will find it maybe very easy and maybe my stupid example. But if I try to see the example code which we had in C, here, the system. So like take a command, execute, send back the status code. I'm not doing enough checkings and putting an expect there, but at least it works. So again, I do Maturin develop, Python, import RustNL, I don't know, det. So the first line is the output from the command. The second one is the 0 is the status execution exit code from the tool. So this was just the start. Like my initial try was only to see if I can replicate what the CPython extension is supposed to do. But from that moment onwards, writing anything in Rust and then having it exposed as Python became extremely easier and easier and easier target. And I have to say, the authors of the toolchains and compiler and everything else in the Rust land is amazing. Like they're spending so much of time and making sure that the experience for anyone new, like I'm writing it for multiple years now, but I'm still counting myself as a new Rust developer. The experience is amazing. You know, how to improve my code slowly in a better way. So I actually do a longer version of this talk. I did a couple of workshops in various PyCons, and I'm doing again one in PyCon Italy in the end of the month. It's 2 hours workshop on how to write those modules, like writing real examples. If I can. Now this example is again random OS is in my GitHub, github.com Kushal Das, but you can check it. But I will just try to see. So we can actually create details here. I'm taking a Python dictionary, which is hash map in our case, inside of the Rust, and now creating a string out of it, returning it back, the add numbers you saw kind of things, then reading a file, example codes which a new Python programmer who is never written any Rust code can read and understand and compile. So that was the goal of writing this, and that works. The more time goes, we see more and more projects getting rewritten in Rust and then consumed inside of Python. But that also enables us to do something even better. As I said, I'm an OpenPGP user. I use heavily these YubiKeys, like one example, one smart cards, which allows us to do OpenPGP operations everywhere. But it's one thing about writing libraries, but the other thing is about having applications which can actually be used by other people. I'll actually demo this code right now, how this looks or works. I hope it will work here. This is the app image of the tool. It's on GitHub. It's all open source code, everything. But the goal is why we are writing these libraries. Why are we talking about? So this application, which will start up now, is actually written in Python using something called PySide, which is the binding to Qt libraries. If you know about Qt, Qt, that's the name. It's a C++ library. It works on desktops and phones also, works in like most of these coffee machines which you see outside. Most probably they have that inside, working. Works on Mac, Linux, Windows, everywhere. And this allows me to write Python code. But now I can use the code I have written in Rust and consume it properly. So as a live demo, I can try to see with typo. RustNL, maybe some example, some password. Creating keys. GPG users here, by the way, GPG and smart card. Okay, I can see a few hands. So you can understand that the way we do right now in command lines and the difference between command line and a desktop app. We did not do the design of the UI. There are proper groups, researchers who actually helped us to build up this UI. And so we can do this, and we need to update the UI. You can see that the screen froze for a function call while it was uploading. And the upload is successful. We have a new key here. I'm not even showing the fingerprints yet, but we can do more things like edit a name of the card. Someone who never used the OpenPGP, like the command line tools, and knows the pain of how much things we have to do, you will not easily understand, like otherwise how much pain it is to do it correctly in one go. But this is the place where languages help us to build tools and technologies for the final end users. Like we are writing this particular project, Tumpa, for like hoping that everyone can use OpenPGP, at least the generation keys and using the smart cards, mainly focused for activists, lawyers, journalists, all of them, so that they can use this. And this now works. You can connect it to any device, and it will have the secret subkeys on this. But at the same time, these libraries enables us to do more. Like, as I said, I work for SUNET, and at SUNET, we have some very specific needs for, again, I'm showing only my example, Johnny can encrypt. And if you know that project name, by the way, if you, like, anyone knows the actual paper? Well, like someone, why Johnny can't encrypt? Search about it. So that was just like, I'm pretty bad in project names, so I thought, let me name my encryption project that. So this is another application which is under our github.com/sunet project. It's called TugPGP. This tool, the goal is that we should be able to create keys securely enough which doesn't touch the disk. The goal, again, we will do all the key operations, but we should not be able to save. The user should not be able to save the key on disk. It should not touch. The moment the operation is done, it's gone from memory and everything. So that's what we do there. It's like, again, you will find it's the same Qt application using Python, Qt, and again, parts of it in Rust. So you can do multiple different things. And I'm just showing my examples, correct? So if I go back, and there is this more examples, which is here. This is, by the way, the PyO3 user guide. Examples, I'm going to increase the font size so that you can read. Can you read it now? So you will find now more, this list is growing over the last 1 year. Anyone use this project called Pydantic? Pydantic 2 is rewritten in Rust. And the author is actually started a new company, if I believe, based on the project. And they are talking about the performance gain by rewriting everything in Rust, still enabling all Python users to consume it. So my goal here, giving this talk to all of you, the Rust developers, is to explain to you why it is important to think while you are developing libraries, that those libraries may not be used only by other Rust developers. Those can be used and will be used, if possible, by people who are from different ecosystems. But we all have to work together. And if I look at this, I'll have one last quote from another friend, Dr. Brett Cannon, who is a Python code developer, also part of the Python Steering Council committee, that way, that he doesn't want to write any more C code outside of CPython. If possible, we'll write it in Rust and consume it directly in Rust, maybe in Python. So that's the future we want. We want people to write better code, and Rust enables us to do that, so we want that. But at the same time, for my case, and I know there will be many like me, where we want other Python developers, people who don't have to think. They will just consume the things already written. They should be able to use the exact same libraries. So if you use something called edge encryption, so there is a Python, oops, that's my phone. There is a Rust extension, Rust library for that, and I use that to create a Python module. In the same way, there are multiple other things which are like originally written for Rust, including RT, ARTI. It's the new completely rewritten TOR in Rust. It's not finished yet, but I'm also working to make sure that we have the Python bindings ready for it in future. I'm working on it slowly, but it's all open source, so feel free to join in. But that's basically my talk is about. If you have questions, I would love to hear. If you want to show me the actual code for Johnny Can Encrypt or any of the projects I have, I can open it up and discuss. So I particularly asked for having more time for the talk, a question and answer session, so that we know we can have some discussion. Otherwise, it looks really scary from standing here and seeing everyone is like looking at you like this. So
thank you. That's absolutely fantastic, Kushal. Thanks a lot. So with that, I would like to open up the floor for questions. Who has a question? Oh, there we go.
Lucky me, one question at least.
Do you think you can throw it? Yeah, so someone's gonna. I'm gonna hit someone. Ah,
ooh,
that's not bad.
Went pretty okay. Thanks for your talk, and yeah, really appreciate the sentiment of let's make it available to everyone. Let's make it available to Python. But I was kind of wondering, what is your experience with marrying Rust's strong typing with Python's, if it fits, it goes, type of programming?
So that's, as I understand it correctly, how does that fit in between the typed language like Rust and then getting into Python? So the easy answer is, if you have seen, like Python developers are getting more and more excited about having type annotations in our code. We want to, not for runtime, but more about readability so that people can read more, do things better. And I'll show you directly from my own example. How to big? So what we do is we write things like this. This is the typing, what do you call it, annotation details for my module. And I know if I write it instead of in something else, it will work runtime-wise. But we want to make sure that the actual consumers, the human being, they get the correct information and it works. Sometimes it's really difficult because coming from a dynamic language background, I am always happy to just put anything randomly. Everything is object. It will just work in Python land. But then while working with something like Rust, where I have to make sure that I'm sending the correct data type. So, and in my particular, this library in multiple cases where I'm receiving either a string or an object, a Python object, and then before calling the actual Rust code, I make sure that in my Python code, I convert it into the right data type, and then send it across to Rust land, get back the answer.
So for your first example, you had the sum to string, and your function took a usize, but in Python it's just an int.
Yes.
And an int can be anything. How's your experience making that work?
I'm yet to find issues with it, and Pio3 took care of the magic.
That's great to hear.
That's the Pio3 magic, not me. Oh.
There we go. Does somebody else have a Oh, no, now it needs to...
Yay!
Good throw. Yeah, so I'm not very familiar with the pipeline, the compilation pipeline of Python, but what I understood from the presentation is you generate a shared object of a sort from the Rust library, and you perform a runtime injection, and you just run whatever is there, right? So
not injection as such, it properly gets loaded. So if I see, where is that? Where does it go? So just give me a second. Yes, please finish the question. Let me show meanwhile.
The question was if you have some way to integrate the LLVM output from Rust into the compilation pipeline of Python, or it's just some runtime thing?
It's the standard runtime Python extension. So if Python knows this is the path, and it will find out that it's something a Python extension, so it will try to load it. So let me try to find that thing. So that's the file.
Yeah, that makes sense. It's clear.
Thank you. It's not anything fancy. It's just the very basic shared object file because Linux. So nothing fancy at all.
Yeah, that fully answers the question. Yeah, thank you.
Thank you.
So, there's a question on the same. Yes. Nice.
Got him. Ruby 3.1 starts having Rust inside C Ruby. Is there Rust coming into Python, into C Python?
So if I remember correctly, there was some group of people tried to write a complete rewrite of Python from Rust, in Rust, from scratch. I think it's called Rust Python or something. Yeah. The C Python itself doesn't have any Rust code inside right now, and maybe not near future, but we will reach there someday, hopefully. Yeah. I'd love to see that.
Yeah, I've been contributing to the Ruby version of rewriting it in Rust, and that's an adventure. Yeah.
There are hands just below.
So we're going to do 2 more questions. And I got here one at the front. So
yeah, and I'll be here for the whole day. So feel free to catch me after the talk. I'll come out if you have questions.
So my question is so if you want to distribute the Rust module, how do you handle build a wheel file I saw? But how do you handle do you build it for different Python ABIs?
Correct. So the question is, how do you handle the Python ABIs, which might be different between Python 3.9, 3.10, 3.11 as such and stuff. So the Maturin itself will take care of it, the tool I demoed. So let's say on Mac, where I noticed for the first time, was if I have more than one Python installed, while building the wheels, it built for all the Python ABI and taking care of it. And on Linux, it's, if I have a wheel here, here you can see that per Python version, how it's doing. So separate wheels for each one of them. I can build many Linux wheels, which I actually do, and that I publish. But that's a separate task. But again, many Linux wheels is something which I inject shared objects, but for each Python version separately. That's
right. Yep.
I think one last question.
How to do panic-free error handling in Pio2?
In
Pio2. I saw a lot of expect and unwrap, And I wonder if there's other ways, because you avoided that somehow, even though it should be easy. Error handling.
So the way I understood people do, my understanding so far, is handle it like, proper Rust error handling. That is, check for error or result, and then if I use my actual code, where are the errors? So you can actually create Python exceptions like this using the macros provided by Pyo3, and then return those. And I can have like implementation for the kind of errors which don't have a corresponding Python exception, and then map out everything so that anything that goes out are, instead of panics, proper Python exception, so that the Python code can handle it. That means you have to write a little bit more extra code to make sure that everything works properly. And you can see that I have multiple errors, just to make sure that it doesn't panic. Perfect. So I'll be available here, and you can still find me on internet. If you have any questions, anything else, that's my Mastodon account, my blog. So thank you for listening to me.
Thanks. So one other quick note on Python and Rust is that if you might be interested in the Mojo project from Chris Ladner of LLVM fame, who is creating a superset of Python that includes typed stuff that's as fast as Rust. Next up, we have Ed Page. Ed Page, you've definitely used his work. You may have used the cargo add command, which Ed finally got into cargo proper as of 1.62. Ed is a member of the cargo team. He maintains libraries like TOML and CLAP and a whole bunch of other stuff. And today he will be talking about improving the test infrastructure that we have in Rust. So give it up for Ed.
So I didn't realize this session is going to be the invasion of the Pythonistas. That'll make sense when we get a little bit later into my presentation. So we're going to talk today about testing. One of the great things about Rust has been the fact that all of your basics are built into Rust. You get dependency management, you get documentation, you get testing. If I can figure out what my click button is. There. So I mean, it's actually pretty simple. You can just it's a very low ceremony. You can just go ahead and annotate your function, do your asserts, just put this in the right files, and it just works. And nothing has really changed since then, actually. Even though that it's not necessarily scaling to what we have today. And that's what I'm going to be talking about. Like, I've been hitting a lot of these pain points. Through all of my projects, I'm regularly interacting with these replacements for the existing cargo, for the existing libtest harness. As a good example, this is what cargo uses. We've basically shoehorned in our entire layer on top, and we have our own test macro and do all these sorts of things. And cargo add was mentioned. To get cargo add integrated into cargo, I had to go and rewrite every single test to switch from how libtest does things to how cargo does things. And that's losing one of those advantages that we have of having that built-in testing, of the fact that, like, in theory, every project uses it, so you can just transfer from project to project and be able to automatically write tests and have it all work for you. That doesn't actually work when you're having to use all sorts of random test harnesses that all do things in different ways and might not even be compatible with each other. So that's one of the, I've been hitting a lot of pain points with that. Also, I think a lot about a Church of Sweden bishop came up with these rules for having discussions among religions. I think this actually has a lot of application beyond religions, like, well, maybe this is religion, Vim versus Emacs, or Rust versus Go. The one I specifically want to highlight is the last one, leave room for holy envy. That's where you look towards the other group and admire the things that they have, even if they don't necessarily fit within you. We were just talking about Python. There's a lot of benefits to static typing. There's a lot of benefits to result over exceptions, but there's some things that work a little bit better in Python because they have those features. That's an opportunity for us to be able to have holy envy for the Python community, to be able to recognize, hey, they have some strengths here. Like, we should be able to admire these. One of the specific ones that I have some holy envy for is how testing works in Python. We look at this snippet of some Python code that I wrote in a previous form of my career, and we've got the ability to inject new command line arguments. We are able to create fixtures, have runtime skippable tests, and it all just works until it doesn't, and then there's a lot of debugging pain associated with it. So, you know, but it is make it pretty trivial and easy to follow what's happening here. So it's like, how do we get this in Rust? How do there's this gulf between what we have today and what you could have with something like PyTest. So I'm going to talk about some of those areas where I've been running into these disjoint things where I'm like, I just want it to be able to work right. The first of these is, it's sliding down as I go. Okay. The first of these is conditional ignores. You look at that function, you're like, okay, cool, that function exists, awesome. It passed. Everything is good. I run thousands of tests in Cargo, and everything said everything was okay, so I know it all works. Well, except it turns out, I wonder how I fix the scroll on this. It turns out that there's actually this short circuit in the test, and you don't know that from just running your test. You think everything works, everything is peachy-dory. Cargo actually does use its custom test harness to take advantage of this, where it uses its macros to, at build time, check to see if Mercurial is installed in your system and ignores your test, and then statically tells libtest, hey, it's ignored for this reason. So you actually do get a nice printed message, but we probably shouldn't be at compile time checking to see if Mercurial is installed in your system. That's a little funky. But in PyTest, this is pretty trivial in that you just say, hey, does the HG command exist? If so, skip the test and I'll report it, and it just works. That'd be great if we were able to have something like that within Python. Within Rust, other way around. So another one is, well, there's a lot of talk of fixtures. Oh, I want setup and teardown. I want PyTest fixtures. We have RAI. That gives us fixtures, right? Well, except I've actually run into a problem in one of my programs where a lot of things that you might treat as a fixture, like, say, creating a temp directory, those on drop will ignore errors because panicking in drop is problematic. And so I've actually run into problems where bugs in my tests were masked because of this, because of weird file system issues on Windows compared to other platforms. And so it'd be really great if we had a way to be able to easily make sure that close was called on all my tests rather than me having to go in and hand put in the close everywhere. That would be a great aspect of having a form of fixture support. Let me just see if I don't know what's going on here. Anyways, Alex, I don't know if you want to just mess with the laptop while I work on this to try and fix this, because now it's starting to go off screen. But we at least see the important part, that we can just, if this were Python, we could just be able to make that reference to a fixture, and we just get it. It'll take care of the teardown and all that stuff for you. Another way that this is able to help us is, thank you. Another thing that ties into the value of fixtures is Cargo, in its test, it has a custom set of tempter fixtures that allows it to create the temp directory for you and actually leak it and not clean it up until the next run of the test. That way, if your test fails, you see all of your test output of why it failed, but you can actually go into the file system and actually inspect the files of what it did, so you can actually be like, oh, that's why, because that's not being printed to the screen, it's on disk. But if you're just using a regular temp directory, it gets cleaned up automatically and you can't see any of that. But then you run into another problem of, oh, it's leaking all of the tests, it's not cleaning up after on the run. So when you run this in CI, it's easy to run out of disk space. So now you want your fixture to be able to help you identify what are all of your tests that take up the most disk space. So if your fixture could be able to, if you could have a tempter fixture and it could report, oh, at the end of test, the tempter was this big, that'd be a great thing. And that's all things you can be able to do when you have a more flexible fixture system than if you just said, oh, RII will take care of it, let's just step away from this. The next one is a lack of data generation for tests. This is taken from TOML edits tests. And this is the most basic way of doing it. You just loop over it. But now, without you having to do something more complex, the naive way of implementing this, you don't have the context of which iteration of the loop this failed on, which input is what caused the failure. And then you also have to make sure that all of your entries are done in a very specific order, because you might have a more complex case before a simpler case, and then your debugness is like, well, if I had that simpler case earlier, it would have been much easier to debug this problem. And sometimes it's easier to get the big picture of, oh, these 5 tests failed. Oh, this must be the common thread between these failures. But when you're having to deal with them serially like this, it makes it so you can't see that bigger picture. Or another problem with this is, well, if you have a bunch of debug output you're putting out to try and figure out what's going on, you're getting the debug output of all of those other runs, and that's just making it harder to cipher through all this. So you might go through and like make macros to try and make this a little bit easier for yourself, or you might just go and write a custom test harness to be able to go do this. And that's where we have some things like try build, which is especially helpful for proc macros, where you can be able to just, hey, here's some Rust code, make sure it compiles, or here's some Rust code, make sure it has a good error message to it. But this isn't a first-class experience in using this. You have to put this in a separate binary. Its output is a little bit different. You have a really weird way of interacting with it on the command line that's not obvious and not reported within the help. And you then also have these magic environment variables you have to set to be able to interact with this. This isn't the regular experience. This is, again, one of those not quite what the promised ubiquity of test experience that you are expected to get. But if this were all in PyTest, this would be a lot simpler. You would just have your function to enumerate all of your test cases, and you just call a function to verify each of those test cases, and you're done. This is all reported. This is all treated as, this will automatically be individual tests reported in your output, and it just works. So I feel like the common thread to all of this is an issue of scaling up as you get to larger projects. Like libtest works great if you're just doing some quick throw together a very simple hello world program, and then but it doesn't when you get into anything more complex or anything bigger, and it requires you to go through some extra hoops before you get to that. It requires you to go through a lot of pain before you invest in these larger tools like writing your own test harness for being able to take care of these things. So what is our path forward for this? As you kind of hinted, I've been admiring a lot of the things that PyTest gives us, and looking through these problems, I feel like a PyTest model actually helps solve some of these problems. So maybe if we could be able to find a way to be able to make things a little bit more PyTest-like, we can actually have these things all unified rather than putting our hands up in the air and saying, well, you get libtest or you get nothing, and you have to go and write it all from scratch. So I've actually been working through this and starting to write a custom test harness that is a proposed new libtest. And it's being modeled to eventually allow it to be able to have a PyTest experience to this. And right now I'm at the point of being able to just mimic be a copy of libtest to mimic. I'm just right now working on the benchmark side of that. That's the only thing that's left before I'm able to start looking at replacing the full libtest. But then my plan for this is, the biggest hurdle to any of this, that last step of merge this into the Rust standard library, that's going to require, that's a large surface area to stabilize. And so there's different things I'm thinking through and going to be talking with the libs team about of how do we allow this to be able to move forward and get stabilized and be able to be used out. And I think that's where I'm focusing on the minimum of what I want to get stabilized is just the API extension points to allow a PyTest crate to be able to be written on top of libtest, and maybe eventually someday we stabilize the rest of those features as well. We stabilize an actual fixtures macro and things like that. But just starting with just providing the programmatic extension points and allowing experimentation on top of that before we get to that point. The other side of this is maybe none of this gets stabilized. But I think one valuable thing from this exercise is actually the fact that this is an opportunity to experiment with the JSON output of libtest, which that's a key thing. So some of you might have heard of the, say, Cargo Next Test project, which is experimenting with how do you actually run all of these tests from your harnesses. And one of the things that's important for that is the JSON output, and there's limitations and problems with that. And the way I've been writing this is I've been writing it so that all of the nice user interface aspects of this are written based off of the JSON output. So I'm dog fooding it, so I'm able to give a better report of, hey, here's what works, here's what doesn't work for this, so we can get that stabilized and be able to move that forward. That's also why I started with the lib test side of things and not the cargo test side of things, so is to be able to help provide that feedback loop to be able to make things better, to help lead in towards the cargo test side of things. So the things that I could see you all could be able to help me with this on is, what do you have Holy Envy for? What have you had experience with that I've not of, oh, they have this thing in this text environment. What could we be able to learn from that to be able to help improve Rust's testing? But also, what oddball test scenarios have you guys come across so that we can be able to make sure we take that in and design an account for that? You could also just help contribute to the project in the discussions, watch what's going on, maybe contribute some features. You can also help me offload some of my work. This is actually my lowest priority right now because it's important for me to finish what I've already started. I've got a couple of RFCs I need to move forward and some features for clap and things like that. This is right now kind of my filler project while I'm blocked and waiting on other things. So that'd be a great thing. Want to go write some clap features? Go for it. And that is it. Thank you all very much.
We're running a little late, but we have time for like 2 questions, so we got 2 hands right there.
So do you think there's any way to improve testing for example, no STD or embedded targets in any way? Because that's something Rust really doesn't support at the moment, while it is a target of the language.
So I personally don't really deal with those scenarios, so I can't speak directly to them, but that'd be a great conversation for us to have separate so we can dig into what the actual requirements are. Either feel free to catch me or just go on the repo and create an issue and let's start having a conversation about that.
Let's do that.
Hello, thanks for the talk. I'm new to Rust, so maybe it's already exists, but do you have the doc test part of the Python?
So Rust does have doc tests built in, so if you do cargo test, it'll just go ahead and test your documentation for you, and it's great. That's actually one of the things that I'm hoping to be able to improve about this is it's kind of like shoehorned in on the implementation side. I'd love to try and use this work to actually make it a bit more first class, which would then help cargo next test and any future cargo test improvements. So yes, it is supported. I hope to make it better with this.
Thank you.
Thanks, Ed. I've definitely run into some of those pain points. It would be lovely to see it improved.
Oh no, I pinned it.
Must be somewhere.
Yeah.
All right.
Okay, next up is Folkert de Vries. There's going to be a lightning talk. We're going to have 20 minutes to take here. We're going to run a little bit into lunch. 5 minutes, it's all okay. So Folkert is an engineer at Tweede Golf, and he works on a project close to my heart. It's about NTP, one of those overlooked things like DNS and routing. Most people think it's just a given, but it isn't. The development of NTP in Rust is going to be super awesome. Take it away, Folkert.
Thank you. Yeah, so over the last year, I've been working with a bunch of colleagues on a project called ntpd-rs, which we think brings NTP into the modern era. So, question number 1, what is NTP? So NTP stands for the Network Time Protocol, and it is a protocol that synchronizes time across the network, down to a precision of about a millisecond. And this may seem like quite a bit of precision. Certainly, no one will fault you for being late to a meeting by a millisecond. And so for individual people, like, that sort of precision doesn't really matter. But it turns out that for any sort of computer network, it is very important that all of the machines on that network are synchronized. Now, the clocks in our devices are sort of okay. They have to be cheap and compact and light, so they aren't perfectly precise, and they will drift over time. And also how much they drift per sort of hour fluctuates based on, say, temperature. And so to keep this thing perfectly synchronized as it needs to be sort of continually updated. And that's what we do using NTP. And there's a sort of 2 main use cases, if you will. The first one is consistency within the network. So imagine you have 2 machines, and they communicate on some task, and at some point we hit a panic. Now, what we want to do is figure out what happened here. What is the timeline that led up to this panic event? And so what we would like to do is turn to the logs of these two machines, look at the timestamps of all of the log messages, and sort of interleave these two logs into one timeline, right? We just sort based on the timestamp of every log message. But that only works when the two clocks are synchronized. They need to be synchronized pretty exactly, otherwise events start happening out of order in this new timeline that we create. And a message might be received before it's even sent. And that would be a terrible debugging journey. The second sort of use case of NTP is in security. So here's an anecdote about, at Tweede Golf we run our own GitLab server, and it turns out that at some point the NTP daemon, so that is the program that does the synchronization, had crashed. And because NTP is very obscure and not a lot of people know about it, unless either it goes wrong or you are in this room, we just hadn't noticed. And so this clock on this machine had drifted quite a bit, so several minutes at some point. And then one day, we went to log in with our two-factor authentication code, and the server rejected it immediately, because it thought that the code had already expired, which is really annoying. You have to SSH into the machine, and you have to reboot a bunch of stuff, but then it works again. So that is really annoying. The inverse of this is way, way worse, where we can trick a machine into believing something is still valid, even though it has actually expired. And this is a big problem for, say, TLS, so sort of the underlying mechanism of HTTPS, which uses these certificates that are revoked at a certain point. And if you can trick a machine into believing that an expired certificate is still valid, you break sort of the whole security model of TLS. So security is a big and important part of this project, sort of the structural security of this whole program. So then, how does NTP work? Well, first of all, to synchronize, we need to synchronize to something. So we need some sort of source of true time. And this is provided by atomic clocks at various sort of locations around the world, and by GPS satellites. And these are a little bit less precise, but still more than enough for what we need to do. So at our office, we actually have a little antenna, which we have to put outside because the office is a Faraday cage. And then we can get this very accurate time signal. Then we hook that up to a computer, basically, and this computer can serve as an NTP server. And this is called Stratum1 because it's sort of directed or connected directly to the source. Then NTP clients can sort of come by the server and ask, hey, what time is it for you right now? And they can sort of distribute this again. So a client can be a server to other clients. And this sort of recurses all the way down to consumer devices. So that's how that's distributed. Then for an individual client, it's very important that you listen to multiple sources, because if you listen to one, you're very vulnerable to either like someone tripping over a power cord and just sort of drift off, or an attacker compromising this one server, and they can then steer your time to either annoy you or actually start attacking other things on your system. So NTP itself isn't that, there's no secrets that you leak, but NTP is a sort of an entry point for other attacks, and so it's still crucial that we get our stuff right. So, why, though, did we decide to implement this in Rust? Why did we re-implement this at all? There are existing implementations. We could just leave that be and not worry about this. Why is it that we implement this now? And I think there's two categories of reasons for this, the social and the technical reasons. So in terms of social reasons, there are existing implementations. There's like 3, which isn't that much, actually. And more importantly, they are maintained by like one person or like a handful of people. It's a very small group. And if those people ever decide to do something different with their lives, then we have a big problem. Furthermore, attracting new people to those projects is tricky, because these are code bases that are decades old. They are C code bases, which means that they also sort of handle their own half of a standard library and a threading abstraction. And then NTP in and of itself is not an easy thing to understand. So these code bases are really pretty tricky, to the point that we didn't actually use them all that much. It was actually way easier to just start from nothing and read the spec and go from there. And then we looked at them for some tiny details from time to time. And so modern languages typically have a much better story around this. Oh yeah, I forgot, like these projects, of course, also have their own custom build system, because you've got to do that in C. And so Rust provides a much sort of more solid foundation for having very consistent tooling and a much better sort of onboarding experience to your project, which is what we're already seeing with our GitHub repository. And then there's also a bunch of technical reasons why a modern language, and in particular Rust, is a really good fit. So Rust is a very low-level language. It's efficient. It's very good at utilizing multiple cores and doing concurrent work. Also, Rust is memory safe, but that isn't so important here, I feel like, because we aren't really doing all that much with memory. It's mostly I/O stuff. Really what we want is no sec faults, which is something that C projects can never guarantee, and we can, just trivially. We get very nice tooling, so we get tests and benchmarks, and in particular, fuzzing is very important here. We open up UDP ports to the network, so people can just sort of send whatever, and we want to make sure that we just handle whatever they send our way and don't panic or cause other weird behavior. And then also, of course, we can use the package ecosystem. So we use like clap and libc and Tokyo, and also actually we use Russell's in an extension called NTS, which adds additional security to this time signal, which means that our code base is just NTP. It doesn't try to implement half of a standard library. It doesn't implement all of this other stuff. It's just the NTP, the protocol, and sort of the I/O. In the end, our project is sort of similar size to the C projects, and that's because we actually have a lot of tests, and also because Rust is sort of line heavy in its formatting. So when you use a lot of open source software, it's also only reasonable that you contribute back, and this has actually been a very sort of fun experience. Certainly for libc, we added a bunch of new sort of like timing related structs. And there you have a couple people that are super bullish on new PRs and are very eager to help you out. So that is a very good process to go through. Can recommend. Also for Tokyo, the process is a little bit longer because there's more sort of decisions to be made, more documentation to write and to sort of get that right. But still, it's very rewarding when you can then later, like Tokyo released a new release a couple weeks ago, and I was able to use some of the stuff I added, which is a really nice sort of full circle moment. Yeah, so we've been working on this for a little over a year now. It started out as a project sort of facilitated by the Internet Security Research Group, who also do a lot of other cool Rust work, and they run Let's Encrypt, which is also in part why they're interested in NTP. So they funded the initial sort of development of NTP, and then an extension called NTS, which adds more security. And then recently we did a security audit, which found a couple of additional sort of weird combinations of configuration that would panic, and we patched those. And we now have an alpha release, and then in the future we hope to sort of build this out into an actual 1.0 release. We didn't quite feel confident yet to sort of commit to that right now, but it's very much on the roadmap. If you are the sort of person, and reveal preference, everyone here likes Rust, if you want to try this out, if you want to replace a bunch of C code with a nice Rust binary, you can. We have made a couple of installers. This is made with a tool called Plutos, which is really nice for generating these installers across multiple targets. The installers are necessary because we do a little bit of like user group and permission stuff, which is kind of, you would have to like Stack Overflow that otherwise, and we take care of it. And please let us know if you do try this out, how it went, what you think about what it does, and the documentation and all of that. It's Linux only right now, but we have open PRs for FreeBSD and macOS, so we'll hopefully merge that soon. Yeah, so that is the talk. NTP is a protocol for synchronizing time over the network. It is essential for security, for consistency and security. So crucial infrastructure. And ntpd-rs is looking for early adopters now. And I'm also happy to talk about this and our other timing work later today.
Very cool. Who's got questions? Over there.
So you mentioned about running NTP continuously to handle clock drift over time. Do you plan to have support for a one-shot mode similar to NTP date, where for systems where that might be easier? And in particular, do you have any plans for like an NTPD library crate that someone could integrate if they want to build small embedded systems that want to do a one-off NTP sync?
So for that latter part, crates should already be available because that is actually convenient for distribution, especially if you want to get it into like Fedora is something we're thinking about. And actually uploading your crates to crates.io makes that process easier on their side. So you can, it's not really made for that right now, and we are not making any commitments about like the API surface for the time being, but that's certainly something that can be done, which we also maybe want to look into for more of our own tooling, to sort of like dogfood that. In terms of one-shot updates, I think you could hack that on, or like build that on top of the library. It's also something that we do. Like NTP will sort of make one big jump if it thinks that is necessary. Like generally, you sort of steer the clock very gently. You speed it up or slow it down a little bit. If you follow like Rust discourse about monotonic time, this is sort of related, where jumping the clock might, like that's not a nice thing to do to a computer if you can help it. Should be fine, but sometimes it isn't.
Yeah, let's go over there.
Earlier in your talk, you said we can guarantee it doesn't panic, yet the security audit, it did find ways in which it could. How do you do that? And how do you get this guarantee before the security audit does?
Okay, I said I guarantee it doesn't sec fault. I see a lot of sec faults in my other work, but we can guarantee it doesn't sec fault in the sense that we use the Rust compiler. We have a little bit of unsafe code around steering the clock and around like some settings on UDP sockets, so they give timestamps to us. Otherwise, it's all completely safe Rust, and so we're very confident that it will never sec fault. Sort of modulo rustc compiler bugs, but you know, what can you do? In terms of no panics, that one is way trickier because it's like Rust doesn't necessarily make that easy. Like a panic can be sort of hidden somewhere in some indexing operation. And even there are actually a couple of places where we do explicitly panic because we consider it sort of better to, if we are ever in a sort of an invalid configuration, we say we're just gonna panic right now instead of continue to steer the clock because we might be doing something completely sort of wrong based on wrong assumptions, and it would steer you in a very sort of very wrong direction, basically, and so we explicitly panic. What you don't want is sort of random panics because people can potentially exploit that to just take down your NTP daemon. That's just like good coding practices, and security audits is kind of the best we can do. I think like there is a way to completely eliminate panics by having the linker do some magic, but that doesn't work for us because sometimes we do actually want to panic.
I saw I think there was one more. Yeah, can you pass it down?
You mentioned briefly Plutos. What is Plutos? How do you spell Plutos?
Okay. Yeah, it's from the Greek. It's I think it's with OU, so it's P-L-O-U.
Yeah, you spell it as Plautos. P-L-O-U-T-O-S.
And what does it?
It takes Rust. It takes Rust code and it builds like Docker images, Debian, and Red Hat packages out of it for different builds. So it does like the last 3 versions of Debian, last 3 versions of Fedora, etc., etc. So Rocky Linux, etc., etc. It's all supported. So you just write the code, and Plautos will take care of doing all of the packaging for you.
It also does like linting and then all of the like, it just takes all of that hassle away from us. We just run CI, it spins up like 100 actions, and then a while later it just works.
Yeah, I think the only other thing I should mention is it heavily relies on GitHub Actions.
Oh, yeah.
So currently it's only supported if your project is in GitHub. We would, there's a lot of interest in this. It's managed by Nelnet Labs. And we would like to also make it available for other platforms such as GitLab. Oh yeah, we take PRs for that. All right, thanks a lot. Then we are the only people standing between you and lunch. Hang on.
But we're standing here for a reason.
Away yet. Don't walk away yet. So about 1/3 of the lunch is served on the 6th floor downstairs, where Mara did her book signing, where the forum was, and the 2/3 of the lunch is where you registered here upstairs. So if you could please sort of spread out and not all stand in one spot, that'd be super awesome. Lunch is going to be until 2, so we expect you back here at 2. Anything else you want to add, Dirk-Jan?
Maybe make it 1:55.
Okay. 1:55, people.
Hey, was the talk okay?
Yeah, it was nice.
Point, like, for the Rust people.
Yeah, I mean, it's good.
Okay.
So for this crowd, it's a little bit more intro level, but it's good. We don't have like.
Absolutely.
It's not a heavy Rust talk.
Yeah, exactly.
It's more about like while you do so, make sure that there are other users.
Yeah,
that would serve the.
Yeah. Hello, everyone. Welcome back. Did everyone get some good food in them? Good. There were some lines I saw, but I think in the end everyone got to have some food, so that's good. Right. Well, that solves one issue. All right, so we're going back to some talks. Here's one of our longer talks from Jonathan. Jonathan was, until recently, a systems engineer at Cloudflare, working on Zero Trust, but he also created the Dioxus UI framework, and recently announced that he's now working on that full time, which is very, very exciting, I think, for the Rust community. So yeah, he will tell us all about Dioxus and how to create cool cross-platform UIs in Rust. Take it away.
Cool. Can you guys hear me properly? Good for the people in the back? All right. Thank you for coming. I hope everyone stays awake after lunch. Lunch was good. My name is John Kelley. As they mentioned, I'm the creator of Dioxus. So Dioxus is a cross-platform UI library for Rust. That's why we're here. For the past year, I worked at Cloudflare on Zero Trust. And like they said, I now get to work on Dioxus full-time. So everything you love about Dioxus today should hopefully get better and well into the future. And I'm super excited about that. So we have a lot of new features planned for Dioxus, some stuff we're going to cover in this talk. And I hope we can release it quickly over the coming weeks and months. My goal for this talk is to showcase a lot of the unique design decisions that went into Dioxus over the past year, so that the community and the Rust GUI authors have inspiration for their own projects. So we're going to do a little bit of live coding, show off some of the cool features, dive into some of the weird architectural decisions that we've made, and hopefully inspire you to go build the 51st Rust GUI library. So with Dioxus, we're on a mission to fix cross-platform app development. There's a lot of stuff wrong with cross-platform app development right now. So in 2023, your users expect a lot. They expect apps that run everywhere. On your phone, you probably have Spotify installed. I pay $15 a month for Spotify, so I expect Spotify to work on all of my devices. I have it installed on my desktop. I have it installed on my phone. I expect it to work on the web, smart speakers, smart TVs, smart watches. Pretty much anywhere with a screen and a speaker, Spotify should work. So if one of you, an aspiring, humble, indie app developer, wanted to compete with Spotify for whatever reason, your users would expect that your app would work everywhere that Spotify works. But there's a big problem. As an indie app developer, how are you expected to maintain an app on every single platform, especially a native app? Across Mac, Linux, Windows, iOS, TVs, you need to know like hundreds of different technologies and like 7, 8 different programming languages. You can't do that. So there are options that simplify this. Not a lot of them are that great. So if you play within Apple's walled garden, then you can get pretty far with Swift UI and UIKit. It seems like a lot of people here are networking, so Swift UI and UIKit are these libraries for drawing apps to the screen on Apple's platforms. They don't support the web, but they do give you pretty decent code reuse across all of Apple's devices. You can share code from your smartwatch to your iPhone to a desktop app. But that being said, you are glued to everyone's favorite editor, Xcode. You need Apple hardware to develop an app, which sucks. And you really can't serve the 3.3 billion people running Android, and surprisingly, 1.3 billion people running WeChat mini apps. So what are your options? If you stick with JavaScript and React, then you have some decent choices. If you're going to build a desktop app, you can use Electron. If you want to build a mobile app, you can use React Native. And you want to do a full stack web app, Next.js has your back. But each of these projects have some pretty big trade-offs. Now, everyone hates Electron because you're basically shipping Chrome just to run like Spotify or a little simple to-do list. So you're bloating your users' computers 200, 300 megabytes per app. React Native is also sort of a challenging development environment. You quickly run into issues with memory usage on lower-end devices. The performance isn't always there. And you don't really have the flexibility to design UIs the way you want. Next.js is actually really good for doing full-stack web development, but you can't really share any of your Next.js code with your React Native app or your Electron app. And that's really the biggest pain here. If you're an indie app developer, you want to share your code everywhere, across all the platforms. If you build a button or slider for React Native, you can't share it with your Next.js project. Some logic can be reused, sure, some libraries. But if you're relying on any sort of native libraries, you just can't get a React Native project to share any code with a Next.js project. Now, there are a lot of options up here. We have Cordova. I don't know if anyone's used that. Xamarin, Tauri, which is a popular one in the Rust community, and Flutter. And I think Flutter is the closest analog to what we're trying to do with Dioxus. So Flutter fits the bill. It gives you a ton of features. It's made by Google, but it has one major downside. You need to know Dart. And I don't know Dart. I don't know anyone else who knows Dart. OK, we got some hands. The Dart ecosystem is limited to Dart. You can't really just pull in a Rust package. There is a really cool Rust crate that allows you to use the Flutter renderer, so you get the entire Rust ecosystem, and you get to render with Flutter. But that's kind of still just this icky system that I don't want to have to deal with. I don't want Dart in my project. I just want 100% Rust. That's why we're here, RustNL. So we want Rust completely in the stack. So we've talked a lot about apps, but we're here at RustNL. We should be talking about Rust, and that's where this conversation is going to go now. I assume we all love Rust. We love cargo, RustDoc, portable binaries, strong type system, no seg faults, all that great stuff. So we have all these superpowers. What is the Rust community's answer to this cross-platform app development problem? Well, until now, Rust's app story has been pretty immature. Obviously, to start building an app, you need a GUI library. If you can believe it, there are over 50 Rust GUI libraries, and yet there's no clear winner. But the ecosystem seems to agree. They've created over 50 GUI libraries. Rust could be an amazing language for app development. Apparently, we just haven't figured it out yet. Maybe the 51st GUI library will solve it. So that begs the question, as a community, how do we get on the same page? What do we need to make a viable alternative to Flutter or React Native? So I personally think the solution that will come out of Rust has to play into Rust's strengths. And it comes down to basically 3 main points. Number 1, Rust can cross-compile basically everywhere in a way that makes JavaScript insanely jealous. You can run Rust on ARM components, x86, STM32, WebAssembly. There's no user or target Rust can't reach right now. Our UIs should be the same. Our widgets and buttons and components should look and feel the same no matter the target. If I spend an hour wasting my time to make a button look pretty for my web app, I want that exact same button to look the same for my mobile app. Number 2, Rust gives us the power to manually manage memory and performance. Authors should be making their libraries so fast that nobody even bothers to look at benchmarks. It's Rust. It scales, it's blazingly fast, even on toasters. We know. Number 3, and I think this is the most important, this is near and dear to my heart, Rust prioritizes developer experience. If you look at a lot of the Rust GUI libraries right now, they have a lot of rough corners. They're not the easiest to work with. They got clumsy APIs. So we can do better, right? We love cargo. We love RustDoc. We love the integrated testing that Rust gives you and the great error messages. So as GUI library authors, we should really be leaning into this and focus on designing clean, simple libraries that make the appropriate trade-offs between performance and development speed. We should be seeking to find a good enough solution without getting caught up in the ideological weeds. So that's where Dioxus comes in. With these 3 pillars in mind, I spent the past 2 years, nights and weekends, putting tons of hours into building Dioxus. So for the rest of today's talk, we're going to dive deep into the design of Dioxus and explore many of its interesting architectural decisions. So at a glance, Dioxus is declarative and component-based. It's inspired by React, for better or for worse, and it uses a virtual DOM. It targets the web, desktop, mobile, the terminal, live view, which is this cool new rendering target, and honestly, a bunch more targets. It has exceptional performance. It's top of the pack. We put a lot of work into making it as quick as possible. It also supports some integrated hot reloading and some spiffy dev tools. So we're going to cover that we're going to cover that in the talk. But if you don't know a whole lot about GUIs and user interfaces, you might get caught up on what declarative and component-based means. When I say Dioxus is component-based, that means Dioxus is made by composing your user interfaces using functions that describe the layout. These functions do things like encapsulate state, handle user input, and they're composed of their own subcomponents. You never really explicitly create individual elements with Dioxus. Instead, you simply pass your RSX markup into Dioxus, which handles the drawing for you. And the mechanism that handles this drawing to the screen for you is called a virtual DOM. So Dioxus, again, like I said, for better or for worse, if you kind of keep up with all the drama in the JavaScript world, uses a virtual DOM. So this is not new in the field of UI library design. React did it, and libraries before React did it. So I'm going to paraphrase React's documentation here. They do a pretty good job of explaining what a virtual DOM is. And this is pretty core to understanding a lot of the features that come out of Dioxus. The virtual DOM is a programming concept where an ideal or virtual representation of a UI is kept in memory and synced with the real DOM by libraries such as Dioxus. This process is called reconciliation. This approach enables the declarative API of Dioxus. You tell Dioxus what state you want, and it makes sure that the DOM matches that state. This abstracts the typically error-prone manual manipulation of DOM elements that you would otherwise have to do for your apps. If you've ever written any UI kit in Apple land, you know how hard it is to keep your UIs in sync with complicated user interaction. Whenever the state of your app changes, Dioxus will render your components. And because components are functions, Dioxus is just simply calling those functions and returning an element. Dioxus assembles these elements into a tree, or a virtual DOM, and determines any changes necessary between the old state and the new state. And then it takes those list of changes and it sends that to a renderer, which knows how to patch the screen and draw your widgets and squares and circles and text. So I've talked a lot. I want to show off some live coding, so you're going to have to bear with me while I futz with the prompter. Cool, so we should all see my desktop. So, everybody can see this, right? Oh, wow, VS Code looks weird. Fun, okay. So this is like the simplest Dioxus desktop app you can build. We import the prelude at the top, typical Rust fashion. In our main, we are using Dioxus test-op, which is a renderer, and we're calling the launch function. All of the Dioxus renderers sport a launch function, which basically takes over the thread that you're on and runs the virtual DOM. When we launch the app, we have to give it a component. In this case, we have an app component. All components in Dioxus are just functions, so they're really simple. You don't need a struct with a derive or an impl. So we can get down to a hello world that is 11 lines of code. And we can code golf this down to 3, but it doesn't matter. It's pretty simple. You call render on some markup. This is typically provided by this RSX macro. There are alternative macros you can use. Hate it or love it, you have to use macros if you do Dioxus. This RSX macro is this sort of weird, custom, funky dialect of Rust that we put together. So if you know Rust, it's pretty easy to build user interfaces using RSX. And then we pass in some markup. So we'll just run our app here. And boom, we have an app. It's pretty quick, too. There are 300 dependencies. Not all of them are us. A lot of that is Tokyo, but you know, don't look too closely. We can iterate on this, so we can create a bunch more header elements. Cool, yeah, that's what you think it does. It's important to note that this is actually HTML and CSS. And that is an architectural decision in of itself. And when I talked about we made a bunch of interesting architectural decisions, one of those is sticking with the lingua franca of the web, HTML, CSS. That means you don't have to learn anything new. If you've been doing web development for 20 years, you've walked through PHP, WordPress, Laravel, you know, all of those technologies, you can keep all of that knowledge you've retained over the years. You don't have to throw anything out. So if you want to build a desktop app, you're still using HTML and CSS. You want to build a mobile app, HTML and CSS. They're not the sharpest tools in the shed, but they get the job done. So we can do things like wrap this header element in a div. And then we can give it a border. And Copilot completes it for us. We can run it. And we got a border. So it's pretty quick. That's just the HTML and CSS knowledge that is imbued in Copilot. So I don't even have to know HTML and CSS to get by. What's pretty cool is because it is just HTML and CSS, we're able to bring all of the documentation from Mozilla straight into your editor. So this is pretty cool. This is going to be magic here for you in a second. If I hover over this H1 element, all of the Mozilla MDN docs are available to me right now. I don't have to go open a window and figure out what the H1 element does. It's right there. And we can even click the H1 element, and it takes us to the documentation. So it's pretty cool, right? Yeah? How many Rust UI frameworks do that? All right. Cool. So I like to be lazy. I don't like this CX.render stuff. I like just render. Cool. Shortens the code a little bit. So this render macro can take a bunch of interesting Rust semantics and tokens. We can do things like attach assets. So, oh, great, Copilot did it. We can add an image tag, and because this is just HTML and CSS, it's an image. This will automatically pull from the file system, and we get a logo on screen. It's pretty easy. Imagine how hard that would be if you were doing this in like anything else. Okay. You can even map like iterators and conditionals in this RSX dialect. So 0, we're going to map it to 5, map I, RSX, and then I. Cool. And then we can see it renders 0, 1, 2, 3, 4. So iterators map in pretty easily. So it's pretty simple to do things like rendering lists. And we can even do things like rendering conditionals. Let me get rid of this. So if true, RSX, or code goes here. Cool, and we have code goes here. So you can see it. So it's pretty simple to compose your user interfaces using the RSX macro. We can get pretty complicated with it. We can even add, let's say, some sort of event handler onto this header element. So we can add an onClick, and then we just print, clicked. Oops, still running the app. So now whenever we click the header, it's not a button, but it's still clickable, we can see that clicked gets printed. So it's pretty easy to add like interactive functionality to your markup. What's important to understand, and we talked about this virtual DOM stuff, is that when our apps are rendered, they're only rendered when we tell them to be. So rendered. In this case, oops, we're still running the app. In this case, we see that the component is rendered only once. And when we click the title, it doesn't get re-rendered. So this exists in React as well. You have to tell React that this component is dirty and needs to be re-rendered. Typically, you go through use state, set state. But in Dioxus, you can just do it explicitly. So we still have this going on. 6.needs update. And what this does is it renders the app the first time to get the stuff to the screen. Then when we click it, we get clicked, printed, and then the app is re-rendered. So when Dioxus goes to reconcile the state of your app, it will take the old state and the new state, compare the differences, it's called diffing, and then send those changes to the renderer. Now, we have no state that is changing, but we do have the component re-rendering. So let's add some state that changes. That's pretty easy. So let val equals cx.useState. This useState method is just a way of attaching some state into this component without having to declare a struct. Explicit state management is done just through these like little creation functions. So this value will be evaluated to 0 when it's initialized, and we can go modify it after the fact. What's cool is that, or use hook, sorry. Use hook. What's cool is that this is giving us a mutable reference to a value. If you've like worked with Rust UI libraries, this might seem just like really weird, right? This is a function. It's not a struct. There's no impl. There's no props. It's sort of like flipping the paradigm on its head a little bit. And we have a mutable reference to some value that we can modify. But what's really cool is that we can map the value into this dynamic text And at the same time, we can modify it, +=1. So you probably won't see this in a lot of other Rust frameworks. There's no clones going on. There's no weird semantics. It looks just like JavaScript. And what we're doing is using the lifetime system of Rust to our advantage. This val has an and mute to some value, right? So this lifetime of the value is actually threaded between scope and element, which means the onClick handler is also sharing the lifetime of scope and element. You don't see the lifetimes because they're hidden here, but if we hover over it, you see this like tick A lifetime. What Rust is doing is aligning the lifetime for us. It's making it a little bit cleaner, a little bit easier to work with. It's hiding some of the annoyances, but we go run the app, it compiles, we click the title, and it increments. It looks like JavaScript, right? It's pretty crazy. I think that's crazy. I don't know about you guys. In practice, you will compose these primitives together. So we provide you the useState hook, val equals useState, which essentially we did that save state into a hook and that needs update. This useState value, the useState hook just combines both of that into this cool functionality. We have to make this mutable. Cool. Oh, and we don't even need needs update anymore. So this is pretty slick. Essentially, we've overridden the += operator, the add-assign operator in Rust, which whatever handle this useState is giving us, it's not a normal value. It's a useState that's generic over some type. In this case, it's generic over in I32. Whenever we do this +=, because we've overridden that trait, that needs update and set state is happening all at once. So a little bit clever, a little bit hidden behind the scenes, but very clean. So again, we got this going on. Cool. So I said before that in Dioxus, your user interfaces are composed of subcomponents. So what we're going to do a thing here. We're going to abstract our state away, and we're also going to clean things up over at it. So we cleaned up our app component. We're going to make a new app component. Scope. Element. We're going to call this one fancy button. Fancy button. And we'll make a bunch of them. So very quickly, in like 5 seconds, I was able to abstract that button component that we had been iterating on and to its own component. And now we have a new app that is rendering for those buttons. And hopefully, if I run this, we should see 4 buttons. Or actually, 4 headers in this case. So, and each one has its own state encapsulated inside of it. So this was pretty quick. Like in the span of like 5 minutes, we spun up an app that has 4 counters, self-contained in their own, little domains. They're like tiny little render loops that are all disconnected, and the state is separated. So if we wanted to share state among these fancy buttons, we would add some sort of props. And if you're familiar with React, React has props. They're just like a blob of values that you can pass in. In Rust, we use a struct fancy button props, text. We'll just use a static string, and we're going to derive partial equal and props. By default, Dioxus requires you to implement partial equal for your props. This means it actually compares your properties when it goes to check if the component should be re-rendered. If the properties haven't changed, the component won't be re-rendered. This is a little deviant from React, which always re-renders your component, and you have to explicitly opt into memoization. With Dioxus, you opt out of memoization. So it's much faster by default, and it's a little bit easier to reason about. I'm going to save the file, and we should get an error. Oh, actually, no. Hold on. We actually have to use the props. So now we get an error. We're kind of abusing Rust like expansion macros, but if you look real closely, we tried our best to give a good error. Fancy button props builder error missing required field text. You can kind of figure out what's going on here. At least we get a strong type system. At least it doesn't compile. Cool. So this will compile. 2, 3, 4. Now in our buttons, we haven't actually used this state yet. So what we can do is hello RustNL. Let's change this to a button real quick. And then we'll put the cx.props.text. Again, this compiles. Everything's working. Cool. you should see buttons. They're small. Okay, we're zoomed in. All right, you get a button. You see how this one says 1, 2, 3, 4. Cool, so we've abstracted state. We're sharing it from parents to children. You kind of get the React model. What's cool is how clean everything is and how it all just like fits together. It's certainly one of the cleanest Rust libraries for managing state out there. Cool. If we wanted to go a little bit cleaner, we totally could. Instead of having this fancy button props struct, we can just abstract this out. We'll copy this text. We have yet another macro. I hope you love macros, because we have lots of. Cool. What this is doing is sort of expanding the function arguments of this component into properties on its own. And we have a bunch of like special cases for things like event handlers and lifetime management that's behind the scenes. It's not as powerful as it could be if you're using a struct definition, but it's very quick to throw apps together. If you go look at some of the apps that are seriously using Dioxus, this is all over the place because people are lazy and they like macros when it helps them out. Yeah, and this does exactly what you think it does. We have our buttons again. This is not the most illuminating demo in the world, but it works, it's cool. There's a lot more like features of Dioxus, but this is like a good overview of the core system that's going on. I think that's it for like this little bit of live demo portion, but I kind of want to show some more interesting stuff. We'll clear out this fancy button real quick. Come here. I have some snippets that are helpful. I said that Dioxus targets a bunch of targets, right? Desktop, web, mobile. Well, you can actually do it in the same file using config. So, h1, hello world. Cool. So on WASM targets, WebAssembly, when we target Rust for the web, it will use Dioxus Web to launch the app. When we're targeting non-WASM targets, like my local computer, it will use Dioxus Desktop to launch the app. So we can run our app. We'll just do cargo run. And we get a desktop app. OK, right? We've been seeing that the whole time. Well, we can do Dioxus serve. We do a little bit of compile. We go to our address. The same app is now rendered in the web. So we've got 2 targets under one code base. So literally, the same code base works everywhere. We can even do mobile. Setting up mobile takes a while, so I have it like prefabbed out. We got our mobile. We have just a simple code base. That is, this is like a to-do MVC. It's like the basic to-do app that everyone stresses their framework with. The code is not necessarily important. The artifact is. So we can run our app. Build succeeded. Great. Live demos actually work. We got an iPhone. Hey, we have a mobile app written in Rust on iOS. And it actually works. I hope it works. RustNL. Oh, cool. It does. All right, to-dos. All right, so yeah, it's typical to-do app. You can hide, complete. Cool. All right, so we got, what do we show? We got desktop, we got mobile, we got web. What else do we have up our sleeves? Well, we have the terminal. I think this one is really cool. This is React in your terminal. And you can hover at 120 frames per second. That's pretty cool, right? The colors change, it's kind of trippy. I've never seen a terminal app that looks like this before. This is super cool. All right. Okay, all right, I'm just like super into that. We also have a web GPU-based renderer. So if you like trippy squares, this one's gonna be real fun. Okay, all right, we're gonna have to zoom in. So this is an HTML CSS renderer. It's not 100% compatible yet. We're getting there. Building a browser takes a while. We have solved CSS layout. So Flexbox, we have a project called Taffy, which has implemented most of Flexbox, a good chunk of CSS Grid. It's not 100% browser compatible. I don't think we'll ever get there. But it's good enough. It's good enough that I can move my mouse around and we can like click on buttons and do things. And this is just all written with like that same HTML CSS syntax. It even has like tab. So you have like tab index, which is another browser thing. So things like doing focusing and that kind of stuff. Even has like keyboard input. So I hit space, you change the color. Pretty cool. We can make it bigger. If you like trippy squares, we got them. It's pretty quick. It's not quite 120 frames per second. It's more like 50 to 60, depending on how many squares you're rendering. We're relying on Velo, which is an API written by Raf Linus. He's like known for Xylem, Druid. So we're kind of leaning on the community at large to implement a lot of these things. This could easily be implemented with Makepad's rendering engine, which is pretty cool. So we're super render agnostic. You don't really care what we're rendering with as long as there is a renderer. We can keep adding tiles. At some point it slows down because we're not running in release. Yeah, we're not running in release, so it slows down at some point. Cool. I have another cool app to show you. This is more of like an app that's being used in production. So this is like top secret. I don't know if I'm supposed to show you this, but it's a full production app that's being shipped with Dioxus today. There are 900 dependencies in this app, by the way, so it takes minutes to compile, but not in incremental mode. Cool. So this is like a Discord competitor. There are chats you can like scroll through. This is a desktop app. We're running in like release mode. We can have favorites. We can unfavorite things. We can go to our settings. It's kind of hard to see. Dioxus desktop supports like pop-out windows, so we can click on our images and cool. So we get a nice, beautiful Instagram-worthy photo. And all of this is done within like the same toolkit, and it works everywhere. I don't think you're going to be like shipping a lot of this to the web. There's some like specific technologies that are using like the desktop type libraries. There's like a federated protocol. But you totally could if you wanted to. If you want to go through the hassle of getting these libraries working on WebAssembly, totally possible. Sorry? Oh, I don't know if it would work in the terminal. I would be super pumped if it did, but I don't know if we can render images in the terminal yet. There are technologies. Yeah, so this kind of just goes to show you can like use Dioxus from the smallest of apps that we like live coded together to the biggest of apps that are trying to take on, major competitors like Discord and Slack and what have you. That's it, I think, for the demos. So we're gonna hop back into the presentation. So there's a bunch of like takeaway innovations from all this work. For one, we discovered very early on that it made sense to batch the changes that we were making to the screen. So when we go to reconcile the old and the new, before we would say the old is different from the new in this particular way, and we would immediately go patch the screen. Now, if your app is big enough, that actually takes a while. It could be on the order of milliseconds. And a new frame could have been requested between the start and the end of that. What makes sense for Dioxus is to batch all of the mutations into a list. So instead of going one by one, we accumulate everything together. And it's actually a lot more efficient, especially when you're operating over in FFI layer. In most of our renderers, the Rust code is not living in the same process as the renderer. So in the case of a web view, the web view window is running in its own process, and your Dioxus code is running in another process, and you have to communicate. If you patched the screen one by one, it would be really slow. So we bunch everything up into like a list of mutations, and we can send it over the network. This is pretty cool because as long as any client implements the Dioxus mutation model, it can be driven by a virtual DOM. So we have a live view client, which is pretty cool, which is the virtual DOM living on a server and a client living in someone's browser. And the server can drive all of the updates to the page without shipping any JavaScript or any Rust down. So just some HTML, a small JavaScript shim layer that implements the Dioxus mutation model, and there you go. You have a client that can operate via Dioxus. We also discovered, and this is important for other GUI libraries that are working in the WASM space, that string interning is super helpful in WebAssembly. If you don't know, Rust stores its strings in UTF-8, but all the browsers store their strings in UTF-16. So anytime a string has to move out of WebAssembly into JavaScript, it has to be encoded and decoded. And if you're doing that a lot, even for the same strings, it gets really expensive really fast. So one thing we discovered, and we're trying to get this out in the air so everybody's really fast, is that you can intern all these strings at that boundary. And we kind of took this model a little bit further with something called Sledgehammer. So we interned all of the strings that you could think of that are relevant to the web model, and we put all of the batching together, and we made it so fast that it's actually faster than vanilla JavaScript. There could just be like noise in the test harness, but it's really cool. It's faster than WASM-Bindgen, which is the library that typically people go through to build their apps with. So Dioxus is not actually using WASM-Bindgen under the hood. We have handwritten UTF-8, UTF-16 decoders with this like Bloom filter and a string interning engine. So it's pretty complicated, but it's exceptionally fast. And you can use Sledgehammer for your own projects. So there's only a few downloads of it, but it's super helpful. Another thing we discovered, and it's not, I don't want to claim the discovery for this. We're sort of building on past projects that prove this, and GPU APIs have done this for a long time, but this technique of double buffering. So React creates a lot of garbage. When you say create element and it creates a tree, there's tons of objects and strings and callbacks that are being allocated. In Rust, we would typically stuff this in a box, and then you're hitting the global allocator a lot, and you're always trying to find out how big the items are before putting them into the heap. And Rust people seem extremely averse to the heap at all. So we were too. So we have our own heap, which is a little crazy, but it's just like a linear swath of memory. So you're going to put a string in, it goes in. You put another string in, it goes in right after that one. And you can sort of assemble these two bump allocators side by side for the old and the new. This is really, really cool because you get steady state memory consumption for each component. And we actually recycle these bump allocators. So your memory usage, at least vis-a-vis Dioxus, maybe not your code, I don't know how bad your code is, but our code is great. Dioxus will only use as much memory as the maximum amount of memory that you've ever used. Once you hit that limit, it will never grow past that. So we can stuff all these lifetimes into this bump allocator, and it's extremely fast. And we get lifetime starting through the entire system. Something we did recently, which is super, super cool, and is being actually copied in the JavaScript world by like Million.js. I don't know who did it first. I think we did, but I don't know. We're actually able to statically analyze the macros, the RSX macros, and figure out what's dynamic in this world and what is static. So when your code gets compiled, we give every RSX call a unique ID. And this is basically just like the location in the code base. We're hashing your Rust tokens a little bit to get that unique ID so we're not colliding. The real features we need are stuck in nightly, and we're not going to run on nightly. But what this lets us do is figure out what parts of the template are static and what are dynamic. And when we go to diff the templates, we only look at the dynamic portions. So in this case, if we see this particular template show up, this RSX call, and we see div and div, we know that's not going to change. And we can make that decision at compile time. So when we go and run, the only thing that gets diffed or checked or allocated, really, is that val entry in the paragraph. So this expands to this like template thing at compile time and a list of dynamic nodes. It's a huge architecture shift, but it's extremely fast. It's so fast that it's faster than like a signal-based API. It's as fast as like Million.js or Inferno. We're not quite as fast as Solid.js, and we're kind of using JavaScript to like benchmark, and we still have this like interning problem to deal with, but it is super fast. It's amazing. We also have auto formatting of RSX, which I didn't show off, but whatever. This is another interesting takeaway for Rust library authors. You can actually use the SYN representation of the Rust token stream in multiple contexts. So if you've written a proc macro before, and I don't know if you have, but they're fun, they're terrible. Essentially what you do is you take this token stream object and you try to parse out Rust tokens into these structs that you define yourself. So you're implementing the parse trait for a struct that you've written. We have a public API for the RSX syntax tree, essentially, the abstract syntax tree, and it can be used in two ways. One, you can spit out the resulting token stream, which is those template definitions, or you can run it through the auto formatter and spit out properly formatted text. So anyone who's doing macros can sort of like steal our architecture, and your users can get properly auto-formatted macros. We have a ticket open on Rust format to integrate some of this, but I don't think that's ever going to be merged. And my piece de resistance is hot reloading. So we'll show this one a demo. The Makepad folks also have hot reloading. Hot reloading is like the hot thing right now. But everyone knows that like compile times suck, unless you're Makepad and they're like 5 seconds. What we try to do is analyze the template at compile time, connect up those definitions we talked about earlier, and watch your code base. If your code base changes in a way that we don't need to recompile the Rust code, we only need to reinterpret the RSX, then we can patch a running renderer. So this is my final slide, but all right, let's pray that this works. Okay. All right. Hot reloading it. Okay. Okay, cool. So we turned on hot reloading. It says connected to hot reloading, right? So in this H1, we can modify our content, and it gets updated live without having to recompile the Rust code. And this is super slick, so, hold on, div. Okay, we need an auto formatter going on. We should get a bunch. We're going to even add new elements. I compile. That's pretty cool. We don't have to recompile anything. Border. Hey, I know some CSS. 1px solid black. Oh shit, there's a border. Cool. So you could like feasibly see how we could like build an entire app without having to recompile it. And this is good for like designers, so we could like build a tool that syncs to your code base without having to recompile the Rust app. The designer can just sit there, plug in all the HTML, add the CSS, and that's pretty quick. You don't have to recompile. That's it. That's all I got. That's all my fun features for the day.
Who's got questions? We got one here.
Well, I might ask you some more questions afterwards as well. Okay. But you showed something about the error messages within macros and them not always being ideal.
Yeah.
Is there anything you need from the Rust compiler to improve that, or can you improve that without that? Is there any way you can make that scenario better?
I would love to see some action on the Rust compiler. It'd be great if we could have like span locations in stable. I think a lot of proc macro authors would care about that. To get really good errors out of proc macros, you need to do partial expansion, which is complicated, especially in our case. So I think part of it is us figuring out partial expansion, or maybe some sort of help on the Rust compiler side for us to build these really good error messages. I think reflection might be needed, but I don't know, not enough.
But do you think you can make this better than it's right now?
I think so.
Okay.
I think so, yeah.
Thank you. What's the accessibility story, if any?
It's HTML and CSS, so you get all the accessibility that HTML and CSS has. You can open inspect element, and you can start futzing around with ARIA labels and stuff. Kind of up to you, the developer, to add those labels yourself. But screen readers work right out of the box, and that's kind of why we did this HTML and CSS pathway, yeah.
So my question is, the live reloading is really nice, but isn't the idea that you put inline Rust code into the render block, isn't that going to really mess that up?
Yeah, so we have to make the decision, can we hot reload this or can we not? And we'll leave this open and we'll add something, 0.5.map, right, rsx. What this will say is, manually rebuild the project to view further changes. So we have to give up in some cases. We try not to ruin your running app, but we do have to give up if you make a change to the logic that we can't fix.
So you serialize the state out and swap it back in a running application?
That could be. We don't have that implemented yet, but you totally could serialize some of the state. It would require your state being serializable, which again requires reflection, but totally possible.
All right.
So as a part-time React developer and full-time Rust enthusiast, this is really cool. Has anyone already built a router for Dioxus?
Yes, and I did it, and it sucks, and someone has rebuilt it, and it's way better, and it should be coming out in the next major release. There are wide open questions on what that should look like. We want to be able to export the symbol and then be able to read the symbol to give you some visualization of your apps router. not there yet, but there is a router, so you can do router-y stuff, yeah.
Okay, cool, thanks.
Weird question maybe, but what exactly is string interning?
Yeah, so say you're passing strings in and out of 2 different runtimes. Sometimes you're passing the same string in and out, and you're incurring a lot of overhead for moving that string between the boundaries. What you can do is hash that string and save it into like a vec or a hash map, and then instead of having to reassemble a string on the other side, you just pull an existing string out of some pool. It's very helpful for like large text blocks. That way you're not paying that serialization cost all the time.
I'm building an app with like web GPU rendering engine. Could I at some point build like a native app that uses the native renderer you were talking about for the UI and has the full power of the GPU without being in a web view, and then still have the app in the browser with like the accessibility of the DOM?
Yeah, that's the dream. It takes a lot of work to get there. You're kind of rebuilding a browser, but that's the dream. And what I really want to build is like a scientific visualization toolkit where most of it is in React, but you get a handle to like a web GPU context, and you can render anything you want into it. So that's the goal.
That would be really awesome.
Yeah.
Yeah, can you pass it back? There's one more question over there that we're going to take, and then we have to move on.
I was just curious, so how does it look on Android side of things, and does it still use Xcode for Apple compilation?
Android works. I don't have Android Studio installed on my Mac, but people in the community have got it working. We're leaning heavily on the ecosystem. The Tauri folks have done a lot of work in getting Tau and Rai, the windowing and WebView engines working on Android and iOS. So we're kind of just piggybacking off their work. But Android works today. I haven't explored with it a lot. I don't run Android in my day-to-day, but I can tell you it works.
Thanks, Jonathan, for your cool talk.
You're the best. Thank you.
Thank you.
No, that's fine. Not that one. This one. Here we go.
Ruben nu toch?
Nee. Yes, Mark, toch? Yeah. Anyway, yeah. Tell me, Mark. Hello.
Hello.
Wow, the technical stuff worked. Switch laptops real quick, and there we go. On to the next speaker. I'd like to introduce Martin Robinson. He works at Igalia, based in Spain, but you got developers all over the world, right? Do you live in Spain? No?
I do, yes.
Yeah, you do? Oh, nice. Martin's going to talk about Servo and the importance of small browser engines and where it's at in 2023 and where we're going next. Thanks a lot. Take it away. I'll run that way.
Thank you. I'm Martin Robinson. Like I've said, I work at Igalia, and I'm just here to introduce or maybe reintroduce Servo to you all. At Igalia, we're working on Servo, and we think it's really cool. So just a little bit of background about Servo. It's a web engine that was created at Mozilla Research in 2012. I believe it was introduced or announced in 2013. And nowadays, it's part of the Linux Foundation. And this is a web engine that's written completely in Rust, like from the ground up. Some components are written in C, like the JavaScript engine is SpiderMonkey. But what's happened over time is that parts of Servo have become integral parts of Gecko and Firefox as time has gone on, in particular the style engine. So it's been very fruitful, like as an experimental, a place to experiment with things and to integrate them into like real web browsers. Some of you may have been a little taken aback when I said that it was a new browser engine. It's over 10 years old now. This was the first commit that was made. And I just want to talk just a little bit about the age of the web platform. So like Firefox
was released in 1997. It came out of Netscape. It has a long history before that with Netscape browser. Some of you may be saying, like, no, I use a modern web browser like Conqueror, the K desktop browser. But what you might not know is that the Conqueror browser is based on Chrome, which was released in 2008. But wait, Chrome is based on WebKit, which was released in 2005. But wait, the KDE desktop browser is based originally on KHTML, the KDE web widget from 1998. So in general, the software we use to access the web is about 25 years old. So in that sense, a 12-year-old web browser engine is pretty young. So when Servo was first created in 2012, it had some really unique aspects. One is that it had process separation. What this means is that the different processes that you use to render web, the different tabs that you had were separated into different processes. So one tab couldn't mess with the other tab, and that really helped with security and with parallelism. The other thing that Servo had was it relied very heavily on the GPU to render the graphical aspect of the page. In two senses. One, when you're taking the different parts of the page, the different divs, you might composite them on the GPU. This was more common in 2012, but also Servo did something special, which was GPU rasterization, which meant that the div itself was not drawn on the CPU, but actually using GPU hardware. In addition, Servo did something where, as it walked down the DOM to lay out the page, it would start spreading that work over the CPU cores, basically allowing the browser to take full advantage, even on one single page, of these massively multi-core CPUs. And because Servo was written in Rust, it had a much greater amount of memory safety than other browser engines, which by and large, apart from maybe the few components of Gecko nowadays that are written in Rust, in C++. This was 12 years ago. I mean, you may be wondering, how does this compare to the state of things now? Because a lot of work has gone into web browser engines. And in general, we can say that process separation is something that all of the browsers you use today take advantage of. Whether it's Gecko, whether it's Edge, whether it's Chrome, they all have a type of process separation. And GPU rendering is much more common. In fact, one of the components that Gecko is using right now from Servo is this web render component, which does GPU rasterization. So this is common now. This is something that everyone has. In the sense, Servo was very forward-looking with these kind of features. Layout parallelism is not something that you have in your browser today. In general, when you lay out a page, it's done on one thread. And there's a lot of intertwining of the different elements in the page that have data dependencies on each other that make this very difficult. On the other hand, there's a lot of work to make this happen. It's a long process. It's happening in browsers that you use, but it's not there yet. Memory safety, on the other hand, is a fantasy. In C++, this is never going to be something that you're going to have in your browser, because recently, the Chrome team released a report saying that 70% of the security issues they face are memory safety issues. And this is because it's written in C++, because a browser is a huge piece of software that is very easy to make mistakes in when you're writing code. So how do we translate those features of Servo into something today that makes it interesting? Well, it still has layout parallelism, and it still has memory safety. These haven't changed. It still makes it unique. But Servo also is in a unique position where it can focus on being a lightweight, embeddable web engine. I know a lot of people have talked today about the pain of Electron. It's a very heavy piece of software, and Servo is not that. So it's in a good position to be this kind of embeddable component. The other thing is that Servo is a much more approachable code base. These other web browsers are 25 years old. They have 25 years of legacy code in them. even something as simple as when I go to edit the code in Servo, the names of the classes match what's written in the DOM specification. This is something that, like, when you're actually working on a web browser is really important and makes it a lot easier to accept outside contributions. Things have changed a little bit around us in the world since 12 years ago as well, and it means that building a web browser engine is a lot different today than it was back then. For instance, the web platform is a lot bigger. It wasn't small in 2012, but there's a lot more web technologies that didn't exist back then, things like WebMIDI, that make the job of building a web engine more complex. There are also fewer browser engines. For instance, the MS-HTML, the Trident engine that we've used, Internet Explorer, is gone. Opera is gone. Essentially nowadays, there's WebKit, forks of WebKit like Chrome, and then Gecko, and that's basically it for our web browser engines. There's been a lot of work on standards, and not just new standards, but also the old standards that we're used to, like CSS2 and CSS3 positioning, which is this describes the basic way that a page is rendered. There were gaps in this before, and you might implement a browser according to those standards, but it wouldn't work the same way as another one because the standards just weren't taking into consideration all the different ways that a web author might write a page. And finally, a huge difference is that, and this is a great thing for the web and for interoperability between browsers, is that there are so many tests, tens of thousands of tests now, and all the browser engines are using them. So theoretically, if you write a browser engine to these tests, then you can be a lot more sure that your browser is going to work the same way. So what are the goals of the project now that we're in this new phase, starting things up again? Well, one is that we want to reduce a lot of friction for new contributions. We want people to be able to come from the outside and work on this project, to be able to implement a web feature, fix a bug, whatever. And this is something that's very different from large browser engines where you might sit down and work for 5 hours and finally get it to compile, and then, okay, now I have to go do this. I mean, we're on GitHub. You can open a pull request. You can use the web IDE if you want. And we're also working on, so we're doing this through better documentation and also making the code a lot easier to understand, simpler, those sort of things. We want to adapt the layout engine to something called fragmentation. Fragmentation on the web is when you take a div or a span and you split it up into different pieces that might be on totally different parts of your display. For instance, different lines for line breaking, different columns for multi-column layout, different pages for multi-page layout. And this is a transformation that essentially all web browsers are doing right now. It's a core integral reworking of how their layout engines work. And finally, because we want Servo to be a really great embedding framework, we're going back to the basics a bit. We want iframes to work really well. Iframes are very complicated. They don't seem like it, but they are very complicated. We want navigation to work really well. We want the DOM, APIs, CSS, OM, we want all that to work well. So yeah, that's what we have in store. So sorry, this was just a quick introduction to Servo. If you want to try it, you can download a nightly build from our website. You can join us and talk to us on this loop. We're always there. We're very friendly. Feel free to file bugs. We'll help you work on a feature if you want to. And you can submit a pull request on GitHub. Thanks.
Thank you. I wanted to ask, are there any questions? And obviously, there we go.
Hi. On GitHub, there are a lot of components of Servo, which are also available on Crates.io. My question is about the future-proofness of those components. Can we assume that they're being maintained? Do we have plans for them? And how many people are working on Servo nowadays?
The future-proof. So you're asking more or less, like, can you depend on Servo? Is it going to be there going forward? Well, Servo is an open source project, and I guess maybe you're asking this because there was this moment in 2020 where Mozilla sort of left it aside. Since that time, there's been people working on it, even with very little money going into it. So it's an open source software that people feel really dedicated to, and it's very easy for people to submit code to it. So in that sense, I think it's unique in that I think that community can sustain it more than other web browser engines.
Any other questions? Oh, there we go. Yeah.
Good throw. Servo is the web rendering engine, right? So in terms of JavaScript support, these sorts of things, is there a JavaScript engine behind it as well?
Yeah, right now Servo is using the SpiderMonkey Java engine. So it has excellent support for JavaScript. It supports all of the modern JavaScript features that you might expect. In general, that's kept pretty up to date. There's an effort to always update our version of SpiderMonkey. So you can expect Servo's JavaScript support to be very, very good.
Cool.
Any other question? Oh, there we go.
Okay, so the question is, after 12 years today, how viable Servo is, if I can put it this way, as a replacement for Electron, let's say, for certain applications that may be ready for using something quite different and new. For example, I'm thinking about the previous presentation, Dioxus, that UI framework. I believe it only renders in something like a browser, right? But could it render, for example, using Servo? And would it have benefits maybe as in application size, speed, portability maybe? Thank you.
Mm-hmm. So yeah, I think there's two components to this which are interesting. One is that Servo is a Rust crate, so in a sense it runs where Rust runs. I'd say the other thing is we're doing a lot of work on layout, but things like WebGL or WebGPU, I think if your application depends on those, Servo might be a good fit right now, and hopefully in the near future for things that depend more on CSS.
Thank you.
Mm-hmm.
Anyone else? Oh, yeah. So let's go for 2 more questions. Rik and you. Okay.
So this is not really a question, this is more an answer to the previous question, and that's regarding Servo and use as a web view. I'm from the Tauri sort of working group, and we are looking to add Servo as a web view target for Tauri. So in the future, that will be a thing. And this is kind of fun, we received a grant from NLNet Labs, so huge thanks.
So
for actually
NLNet.
NLNet, was it NLNet? Yeah. Okay, never mind. But still, huge thanks to them for actually having people work on that. So if you're into that, interested in that, it's going to be exciting.
All right. I'm never going to make that.
Oh, wow.
So, question about modularity.
Yes.
So if I leave the JavaScript engine out and just render bare HTML and CSS like a Wikipedia page or something, I don't think it uses any JavaScript. How big would it be to compile it and use it? How long does it compile? How many crates? Can I leave the JavaScript out at all?
Right. Nowadays, you're asking like, if you could just leave some part of the Servo aside to make your build a little bit smaller. I don't think there's that capability right now, but that does sound really interesting. And
I mean, for instance, for Dioxus, I would say if you write the code in Rust, then you could theoretically just use the HTML, CSS, or layout and render engine.
Yeah, no, that's true. In a sense, it's a little tricky because CSS usually includes CSSOM, which is essentially hooked more or less like into the DOM. But I mean, there might be, like I said, Servo is a great testbed for new ways of using the web. And I think that if you're going to do an experiment like that, Servo is a great place to try it out. And I'd love to have more conversations about that.
All right, thank you.
All right, thanks a lot. And please give a warm round of applause.
Thanks.
And as the next speaker, I would like to introduce, just before the break, Ruben Nijveld. He works at Tweede Golf as well. He's been working on NTP for a bit, for the last couple of months. But now he's going to embark on a new project, which was just announced by Prossimo. Prossimo is the initiative from the IS4G. You may know them from Let's Encrypt. To make some of the fundamental building blocks that we all rely upon memory safe. And Ruben will tell you more about that. Let me conjure up your presentation, sir. So, that was quick. Oh, even that works.
Nice.
Take it away.
It's up. Good. So I'm Ruben Nijveld. I work at Tweede Golf, like Alex just told. So I want to talk to you about sudo. And, well, to talk about something, we should know what it is. So I think probably everyone knows what sudo is. But in case you don't, say, for example, I have this file here, hello.txt, and it is only owned by root, and no one but root can access this file. Well, if I do this as another user, for example, I do a cat of that file, so I want to see what the contents of that file are, I get an error saying, okay, you can't do that. And then I put in front of that command, I put sudo, and then suddenly it asks for my password, and all of a sudden I can see the contents of the file. And for those of you that use Windows and stuff like that, maybe look at this comic. And if you haven't seen this comic before, then you're one of today's lucky 10,000. And if you don't know that reference, you should look that one up. After my talk, of course. So that sandwich thing, funnily enough, the original sudo implementation actually uses the sandwich as a logo since that comic got so big. So this is now the official sudo logo, which is amazing, I think. So we are rewriting sudo in Rust, and with we, I mean Tweede Golf, together with Ferris Systems from Berlin. So we are not re-implementing the entirety of sudo. We are building a drop-in replacement for just the common use case of sudo. And as Alex said, we are being financed by ISRG, so the makers of Let's Encrypt. So yeah, why would we re-implement sudo, of course, is then the question that's best to ask. And well, the original sudo implementation is now over 40 years old. It was created at a time when BSD 4 point something, I think, was just around the corner, which is like somewhere in the early 1980s. Linux wasn't even a thought, so there couldn't possibly have been any forethought in how to support Linux because it didn't even exist. It's all legacy, built upon legacy, legacy defaults, legacy features, all kinds of stuff is in there. And of course, all this stuff is written in C with lots of strings all around, stringly typed interfaces, strings everywhere. And of course, we all know how beautiful C strings are. And the final thing to know here is that sudo is a setuid program. And what that means is that sudo doesn't run as the user you are executing the commands to. So you're saying as user X, okay, I want to run this, but instead it gets run as the owner of the file. So for sudo, this is root. So even though I'm not root, I can run sudo, and sudo itself will run as root. So that means that this program, which is basically a privilege escalation bug all in itself just because it's setuid, and on top of that, there are lots of bugs in the Linux kernel where setuid programs can cause all kinds of weird behavior. So one of my colleagues, for example, just found out, I think 2 weeks ago, that there is a bug in the Linux kernel with Bluetooth handling. So yeah, lots of stuff that could go wrong here. Yeah, and the thing I want to say, all of this may sound really bad about sudo, but the original maintainer, Todd Miller, is actually a really good guy, and he really tries to make this thing secure, but just the history is catching up. And this work has been going on for 40 years, so yeah, I don't want to play down on sudo. I just want to try and get a better implementation using our modern tools. So of course, the thing that I should be talking about, because this is Rust after all, is yeah, sudo has had its fair share of buffer overflows, and modern tools such as Rust, and of course helps make all that stuff a lot better. And yeah, surely the memory safety thing would be the key reason here to re-implement that. And for the ISRG, this is definitely the case. But as we are re-implementing it anyway, there's more stuff to sudo. So there's actually quite a lot of stuff in sudo that you might not expect. So did you know, for example, that user and group names are matched case insensitive by default, whereas the whole rest of your Linux or BSD system will do everything case sensitive? Kind of weird. Did you know that you can use globs and regedges in specifying which commands you can run? So for example, here I have a file or a line in the sudo-rs file that says that I can echo files from var log something. But actually, this is not doing what you think it's doing, because a glob in this way is actually allowing any number of arguments after this. So this means that I can just echo, say, for example, some file from var log, and then after that I echo etc shadow or something, and then this is all fine according to the syntax. So did you know that sudo can actually store all input and output that comes from a command that was run with sudo? And this all contains lots of scary features, such as using regexes to filter out passwords that were input through standard in. Lots of great stuff. Did you know that the sudo-rs syntax actually has lots of syntax concerning host names? So every line in the sudo-rs syntax can actually be filtered out based on a host name. So you can have one sudo-rs file distributed across multiple hosts and then have different sets of rules for every different host. Interesting. Did you know that when you type an incorrect password, you can ask sudo to insult you? Yeah. Great. So for example, this is one of those insults. My pet ferret can type better than you, and there are lots worse insults in there. And did you know that each and every one of these settings I can change on a per group, but also a per user, but also a per command basis? So each and every one of these settings and lots more settings can change based on anything at all. So I have this little gem. So say we have the user Ferris in our system, and here I say, okay, if you're the user Ferris but typed in this really weird way, then we should stop matching case insensitive, but instead match case sensitive. But then is now Ferris allowed to run the command, or is it not allowed to run the command? Because if this matches, then it should no longer match, because then the case insensitive matching should no longer apply. So this is turning into a nice circle of thought where basically, yeah, we don't know the answer. So really, all I'm wanting to say is memory safety is just a start, and re-implementing sudo has lots of other advantages as well. Yeah, so the thing, of course, that I mentioned already, we can get rid of a lot of legacy stuff. There's a lot of stuff in sudo that you don't need in a modern system. So for example, PAM, the pluggable authentication modules, which is available in basically any Unix system these days, you can use that instead of having all these custom authentication methods in sudo. So you don't need anything else anymore. For example, NSS, the name services switch, I believe it's called, which is in libc, basically glibc and other libc variants have the same thing. So you can use this to get your user from another location than just the etc passwd file that is on your system. So you, for example, you could get your users from LDAP or stuff like that. So we don't need to build all this LDAP integration anymore, or at least we could, but yeah, not needed that much anymore. So yeah, we can get rid of a lot of old stuff that you don't need anymore. Yeah, we can leverage the Rust type system a lot. Of course, we can use enums and new types to prevent mistakes, whereas sudo uses all these strings or void pointers or stuff like that all over the place. We can use strong typing to get a lot better strictness about what we accept and what we don't accept. And we can also define new interfaces for modern systems. So sudo has a plugin architecture, but those plugins were defined in like the 1990s somewhere, and they don't make much sense these days anymore. So we can look back at the past 40 years and we can say, okay, given what happened the past 40 years, these are the logical boundaries to have for a modern sudo implementation. And we can also think about alternative configuration formats, because as I showed you on the last slide, there are some weird things about the sudoers configuration format. And yes, we have heard about doas. So doas is the OpenBSD alternative to sudo, and it has a different configuration syntax. And yeah, one of the things we might look at is actually also implementing that configuration syntax. But this is future work, of course. Yeah, so we could use your help, because right now we are still working on getting the basics working. We have a sudo that can run commands and that parses your sudoers file. But we love to know about any non-standard usage of sudo, because yeah, most people will probably ever only run into sudo when you need to do something as root, and just run it as root, I don't care. But there are lots of alternative ways you can use sudo, and we'd love to know if there is anyone that's using sudo in such a way. And similar to that, we'd also love to know about any non-standard sudoers files. So we've all seen the sudoers files in distributions such as Debian or Fedora, but we'd like to know about sudoers files that aren't those standard sudoers files as well. Yeah, so that's what I wanted to say. Thank you for listening, and if there are any questions.
Oh, that's great. There's a question right there. There you go.
Nope.
Try again. Just keep going.
So, are you going to keep the name sudo, or are you going to rename it because you might not want to have everything backwards compatible?
Yeah, so the question was if we are going to keep the name sudo. So for now, our package is called sudo-rs. But the binary that we are producing will be called sudo, because we are, in the end, trying to be a drop-in replacement, at least for those common use cases that yeah, people are used to using sudo for. So at least for those cases, we are trying to be drop-in, so we're trying to keep the name for the binary at least.
Okay. Hi. I saw earlier, like in the slides, that you pinpointed the fact that sudo runs as root as a downside. But I do not understand how would it work without this feature. You know what I mean? No.
Sorry, no, I didn't catch the...
So like in the downsides that you presented us of legacy sudo, yeah? There is basically like set UID. Yes.
Right. Oh, yeah.
So this allows you to run the program as root.
Yeah.
But I don't understand how would you circumvent that? How would you avoid that?
No, we're not trying to avoid being a set UID binary.
So it's like, okay, so it's more secure because it's Rust, so it doesn't...
Yeah, definitely. Yeah, so the thing here is, and this is also something that takes some time for us, because most Rust crates aren't really being made for running as a setuid binary. So lots of things we can't really use because were made for different circumstances, for different use cases. So yeah, it takes some time for us to re-implement this properly. But yeah, having this C binary right now, which is sudo running, which has all these problems, or which at least could be better in some ways. Yeah, that's what I was pointing at there.
Do you have any plans to rewrite System D after that?
No, definitely not. Good luck with that.
I can reveal that I think the ISRG has some ideas about building like a distribution that's free of memory unsafe code. So at some point they'll need something to fulfill that role. So who knows?
The thing here also, and then this is the same like with, for example, we're using PAM right now, which is the pluggable authentication modules. And this is written in C. So, I mean, we're still using some C under the hood somewhere, but wanting to replace PAM means that you still have to keep that C interface layer, because right now there is no stable ABI on Rust. So it's really hard to do this without having more support from the rest of the Rust ecosystem.
Have you thought about adding BSD-ALF support in addition to PAM? And the basic difference is that PAM uses shared libraries, while BSD-ALF uses standalone executables.
Yeah, currently we're a Linux-only implementation, so right now we're not doing that because supporting BSDs actually takes a lot more than just changing the authentication mechanism, because there's all kinds of libraries that we need to use which are Linux specific or BSD specific. So yeah, that's right now that's not in our working plan, so that's not what we are doing right now, but we definitely want to keep it in such a way that we can add this eventually along the road somewhere when yeah, there's time and money and whatever.
Okay, thanks.
Okay,
do we have time for one more, or?
No, I think we should unfortunately go to the break and then find Ruben in the halls if you want to ask more questions. Thanks, Ruben. Okay, so time for another break. Last break before the last set of talks. You know the drill. There's some food or cookies and water downstairs and upstairs. So spread yourselves and be back at 10 past half.
10 past. Nice.
Zullen we dit nog laten checken door?
Ja,
hallo,
ik
hallo, hallo, hallo.
Nee, misschien niet. Ja, die
Misschien is de batterij leeg of zo?
Te veel. Ja, ik loop wel even nog over.
Oké.
Ja.
Hey, yes, nice to meet you.
Nice to meet you. Just once.
Yeah, we tested your slides this morning, okay. So it should be fine. Okay. But if you want to try it out, try the clicker or something.
Thank you.
soon as we hit play, it'll start counting, right? Yes. Go okay, and now I escape and I hit play. Yep. And then as soon as you hit next, it starts counting. I got your perfect little setup. Would you like to get a mic? I mean, this thing works on fine with that. Okay. It's your preference. Not to be moving around. No, exactly. Some people like to be untethered. So there is a clicker if you want to use it, and you can also use the arrow.
Chick, chick, chick. Hee hee.
Nice. Okay, but this is perfect for you. I promise it'll show the presentation. Well, I mean, I get it. Yeah, exactly. Well, see. So, okay. Yay. Dankjewel.
Right.
Waren er batterijen, hè?
Nee, dat was een draadje losgekomen. Waarschijnlijk is hij hier dan toch. Ja. Maar we zijn er weer.
Okay, super good, thank you. Okay, then I'm going to quickly get some of the drink. And please rearrange it in whichever way you want. Thank you. Nice. Ik heb hij is nog stuk, hè? Er is een draadje los. We hebben hem net gemaakt. Dat was zo hard gegooid.
Zijn jullie van plan om alle slides te uploaden?
Alles wordt opgenomen, dus de livestream nu. En alle talks worden allemaal opgenomen, alle video's worden op het YouTube kanaal gezet en alle slides worden beschikbaar gemaakt.
Perfect, bedankt.
Cheers.
Een klein detailtje op doen. De borrel straks is gewoon volledig in de foyer. Dus misschien een beetje voorzichtig, maar het is niet, daar kan niet op de 60 geborreld worden.
Nee, gewoon alles gewoon boven. Oké, maar goed. Ik heb niks over gehoord. Nee, maar volgens mij ging een analyse het...
Ja, het risico. Ik zal even kijken dat dat is.
Oké. Ja, helemaal goed, dankjewel. Thank you, thank you. All right. It looks like we almost have everyone seated. I want to thank you all for being so on time. Keeping a schedule with so many speakers and such a long day is always a little bit tricky, but we're still pulling it off. I hope the break was nice. 2 more talks, and then we're gonna have drinks. The drinks, and God knows I need one. All of the drinks will be upstairs, so this is not in the foyer downstairs. That that'll be drinking and mixing in a library. That could get ugly. You never know. Next, I want to introduce Nicholas Nethercote, who's going to talk to us about the status of rustc. Thanks, and take it away, please.
So the starting point for this talk is that the Rust compiler is slower than we would like. Thanks to a lot of work by many people, it's about 3 times faster than it was when I first started working on it in 2016, but people still complain. Unfortunately, speedups are getting harder to find. Today, if a new contributor says, "How can I help with compiler speed?" I don't really have a good answer because all the low-hanging fruit is gone. There are no easy optimization tasks left. But there is one large piece of high-hanging fruit, which is parallel execution. Now today, when you compile your Rust code, you're already getting quite a bit of parallel execution. The first form is inter-process parallel execution. When you run cargo build, cargo will launch multiple rustc processes, compiling multiple crates in parallel. This works well. Try compiling a large Rust program from scratch with the -j1 flag, and it'll probably take a lot longer than normal. But how well it works depends on the shape of the crate dependency graph. You can visualize this if you run cargo build with the -- timings flag. It produces a chart that shows how all your crates were compiled. This image shows the first 31 crates compiled while building ripgrep. Each line represents a different rustc process. If 2 crates are independent, they can be compiled in parallel. And in this image, there are no dependencies between crates until we get to the last few at the bottom. This run was done on a machine with 28 virtual cores, and you can see that there is enough parallelism here to keep it fully occupied. Now this second image shows the last 31 crates compiled for the same program. There are a lot more dependencies between these crates. Now the compiler can overlap compilation of dependent crates somewhat, thanks to a feature called pipelining. But even still, there is much less parallel execution happening towards the end of compilation. And this is typical for large Rust programs. So cargo will only take us some of the way. For more speed, we want parallel execution within each process. So this takes us to the second form of parallel execution in the compiler backend. The compiler's front end produces multiple chunks of LLVM IR, which are called code gen units. The compiler's backend uses LLVM to process these in parallel on multiple threads. This is more fine-grained than the inter-process parallel execution we saw before, but it is still fairly coarse. Let's see it in action. This is a screenshot from a profiler called Samply. Each horizontal line represents a thread's execution over time. The bottom line is the main thread. On the left side of the vertical red line, you can see the front end is running on the main thread by itself. On the right side of the red line, you can see 16 threads that are created for LLVM code generation. And these provide a good amount of parallel execution. So the back end is already covered. Now we want to introduce parallel execution to the front end. Now there's code for this that has actually existed for several years, and a lot of it was written by a contributor named Dioxus. The code uses Rayon to produce very fine-grained parallel execution. But the Rust compiler that ships today does not have this parallel front-end code built into it. If you want to use it, you must build the compiler yourself with a special flag set in the config.toml file. And even then, the compiler front-end runs single-threaded by default. You need to use the -z threads flag to turn on multi-threading. And at this point, you might be wondering how all this works. The compiler has an internal crate that defines several important operations that enable parallel execution. These have familiar names like join, parallel, par-iter, and par-for-each. In the parallel front end, these operations use Rayon to execute code in parallel. In the serial front end, these operations degenerate to serial execution. And these operations are used at certain key places in the compiler where parallelism is available. The same internal crate also defines several types that support parallel execution. Each one also has 2 implementations. The parallel version of each type provides some kind of synchronization. The serial version does not. For example, we have a reference counting type called LRC. In the parallel front end, it's a wrapper around arc, and in the serial front end, it falls back to a wrapper around RC. We also have locking types. In the parallel front end, they are wrappers around mutex and rwlock. In the serial front end, they fall back to refcell. And there is a similar story for atomic types and iterators. And finally, in the parallel front end, we also split some global hash tables into multiple shards to reduce mutex contention. So that gives you a rough idea how the front end parallel execution works. This is a big change to the compiler and has some risk, so we need to be careful with our shipping strategy. Right now, the shipped compiler front end is serial. Step 1 of this strategy is to ship the parallel front end in nightly, but still run single-threaded by default. That way, enthusiastic users can try it with multiple threads just by setting the -z threads flag. And this is the step we're currently working on. One wrinkle is that the single-threaded parallel front end is unavoidably slower than the serial front end, but we want that overhead to be as small as possible. A couple of months ago, this overhead made the compiler about 6% slower on average. Today, that number is closer to 2%, which we think is probably acceptable. There are still some bugs to fix as well, but we hope to ship step 1 in nightly in June. A contributor named Sparrow Lee is doing most of this work. And then after that, step 2 would be to change the default number of threads to something greater than 1, which will make the stable compiler's front end parallel by default. The timeline for this step is not yet decided. There is another complication though. We do a lot of performance tracking for the compiler. We have a comprehensive benchmark suite that is run on every merge, and people regularly triage the results to catch regressions. And the complication is that the parallel front end makes this harder. First of all, it means we need more measurements. We currently have over 40 programs in the benchmark suite, and we measure each benchmark in multiple ways. First, there are 4 different profiles: check, debug, opt, and doc. And second, there are multiple scenarios relating to different ways of using or not using incremental compilation. This means we measure between 10 and 13 compiler runs for most of the benchmarks. The parallel front end potentially adds an extra dimension of measurement, which is the number of threads. If we measure multiple different thread counts, the suite will run more slowly. It also means that there are more measurements to interpret when deciding if a change is an improvement or a regression. Now, you might think these problems are relevant for the parallel execution already present in the back end, but that's mostly handled by LLVM, and we only update the LLVM version every once in a while. In contrast, the front-end code is changed every day. And there's also another problem with performance tracking. Parallel execution in the front end makes the choice of which performance metrics to use more difficult. So wall time is the most obvious metric because it measures what users directly perceive, but it has high variance, which makes it hard to detect small changes in performance. So our primary metric for performance tracking is instead the number of instructions executed, which has much lower variance. Now, this is a poor choice as a performance metric in the general case, but it works well when most comparisons are between two extremely similar versions of the same program. But that basically assumes serial execution. With fine-grained parallel execution in the front end, the usefulness of instruction counts is less clear, and time will tell if the current approach will need adjusting. So to summarize, I've talked about three kinds of parallel execution when compiling Rust code. We already have inter-process parallel execution via cargo. We already have intra-process parallel execution in the back end. And we're working on parallel execution in the front end. And we hope the first version of this will ship in nightly in the next month. Thank you.
Who's got questions? Okay, that's quite a ways up. Let's see how far I can get.
Could you go back to the slide with the code gen units parallelism, the yellow chart? What is the reason for this stair-step pattern? Is that just the overhead of trying to spawn each thread one at a time?
Yes, so I think the question is about why is there that staggered staircase shape? Yeah, so I believe the main thread is spawning off those one at a time and having to do a bit of work each time. And so that's actually the current serial compiler. If you look at, if you have the parallel front end enabled, like say you've got 8 threads enabled, the first 8 of those staggered steps actually end up getting all shoved to the left because the front end itself is then parallel. It can spawn off 8 of those immediately or almost immediately.
Right.
And so,
but I was thinking, could this be changed without needing to make any other changes to the compiler? Could these threads be spawned ahead of time in the front end so that by the time we get to the back end, they're ready to run?
So I'm not sure if it's the spawning time that's the problem, but there's a certain amount of work preparing the codegen unit or something else. I mean, I don't know. I only just discovered this graph like a couple of days ago, and so I was quite intrigued by it too, and I want to do a little bit more investigation to see if there is some room for improvement.
That's great. Thank you.
You want to throw it?
Where is it?
There's one over there.
All right, can you hear me? Yeah. Is the resulting binary the same between the serial compiled and the parallel compiled?
Sorry, I didn't catch
So
that.
the result, so you compile with your release build, and is there a difference in the resulting binary between the one you compiled with the serial front end or with the parallel front end?
I see. So will the resulting binary be different depending on which version of the compiler you use? I think, off the top of my head, I think there should not be a difference.
So you said that benchmarking this is quite difficult, of course, the parallel version, and but you mentioned that only a single-threaded version of the parallel compiler might be about 2% slower. Is there any indication how much faster a parallel front end will, like rough numbers, right?
Yeah, it's not as good as you might hope at the moment. It's like sometimes it's slower. Well, first of all, it depends on how many threads you try, 2, 4, 8, or whatever. For the moment, I'm focusing on smaller numbers because let's not worry about 64 until we're getting 2 or 4 to be good. Sometimes it's on a good case it might be 10 or 20% faster. Sometimes it's slower, but I think really we need to get that step 1 and get much wider use of it, because the fact that you have to build it yourself means that it's getting very, very little use. And so I think that's an important first step to...
And then maybe more optimizations are possible.
More people can try it out. We get more feedback about which cases it works well with and so on. So
All right, if you could go back to the slide with the decrease in compilation time, it was at the very beginning. Yeah, there we go. I was kind of wondering what happened between version 1.52 and 1.55.
Where the orange one goes like that?
Yeah.
I think that was one of the releases where incremental compilation was disabled due to bugs.
Oh, okay. Yeah,
Because
that
I
makes
think,
a lot of sense.
Yeah, I think the blue one is not incremental, so it was unchanged, and the
Yeah.
other three were different forms of incremental.
Yeah, makes sense.
Yeah.
Thanks.
You can throw it there if you want.
Uh-oh.
Yeah, you'll be fine. See?
Thank you for the talk.
Yeah, it's good that it's soft, right? Yeah.
Yeah, so thanks for the talk. So in relation to the other talk before, where we talked a little bit about the holy envy, have the team considered looking at other approaches and maybe doing a larger re-architecture? The reason I'm bringing this up is there's the Jai programming language by Jonathan Blow, where he architectured his compiler from the ground up to use work stealing, basically, so that whenever it's waiting for type resolution or all kinds of different things throughout the compilation process, it can pick up some other work until that's resolved, essentially in a future style. Has there been any consideration around doing something like that?
Yeah, it's a fair question. It's not something I tend to be a person who's like really good at squeezing the small wins, and then other people are like the big picture, let's rewrite it from scratch kind of people. And I'm not that sort of person, so there are certainly ideas. You can do things like, let's start at the end and work out exactly what, only compile the functions that are going to end up in the final binary, and that way, because you can imagine a lot of library crates, you compile a bunch of stuff, and then the final binary only uses a small fraction of that. And so, like trying to do sort of a data flow backwards kind of thing is an idea that has come up. And really incremental compilation was meant to be like the big thing, right? And it's sort of like, it works reasonably well, but there's also some problems with it. So it's not something I've given a lot of thought to. And given that this exists and it kind of works more or less, it's kind of the one we're going with now. But the compiler's a big program, and like that sort of re-architecture would be a multi-year thing, which is a challenge to think about.
Thank you. So 2 more questions.
So, well, first of all, thank you for your hard work improving the compiler, because even though we still complain, with all these regular blog posts, how to speed up the Rust compiler and all that. So, I was recently working on the Queen library together with Dirk Jan, and we were discussing whether a particular change was beneficial for performance, because right now the library doesn't have maybe let's say the way you're doing it with the compiler, it's very structured, and there's this infrastructure you have put in there to assess the impact of changes. What would you advise as a starting point for library authors who want to incorporate that in their workflow?
So you're asking about if you want to do performance tracking for yourself, like how?
Yes, there's lots of libraries in the ecosystem that would probably benefit from it.
Yep.
But it seems like a very
it's a very intimidating topic, and people have very strong opinions about what's the right way to do it and the wrong way to do it. My take is that mediocre performance tracking is a lot better than no performance tracking. I mean, if you do it completely the wrong way, then yes, you'll end up wasting time. But even if you do something that's okay, and just start with something that's okay. And like the one that we have has evolved over the years, and the choice of benchmarks has changed, and the metrics have changed, and so on. But you've got to start somewhere. So just get something that seems okay. Start there, see how it goes, see if it feels like it's actually making a difference, and then gradually try to improve it. That's what I would do.
Thank you.
So this flag that you mentioned at the beginning, we have to build our own compiler to try it out and actually see if there's a difference. Is there any other
thing where people can, any other flag where we can try out the difference and provide feedback on whether it improves or not?
So the config.toml file, which dictates how the compiler is built, has lots of things in it. It's probably got dozens and dozens, maybe even over 100 different things, and I've only seen, some small fraction of them. So the answer is yes. Whether or not, how many of these would be interesting to sort of general people, I don't know. But if you do actually want to just look at the code, it's in the root directory. There's one called config.example.toml. I think it's got all of them in it, and each one's got like a comment explaining what this flag does. So if you want to check that out, you can do that.
But in the non-nightly, in the stable channel, there's no like similar other flag that you would appreciate feedback on?
None that I am interested in, but there might be other people, other compiler developers who have flags that they're interested in.
All right, let's end there. Thanks, Nicholas.
Let me do some.
Next up, we have Daan, a member of the Dutch Rust community who has given multiple talks at meetups before and usually has something interesting and to say, and also says it in an interesting way, so that's always great. And based on the description of the talk, I think we'll get more of that today. So yeah, I think this will be a great talk to round out the day. And take it away.
Thank you. So, being the last speaker of the day is an honor, but also a bit daunting because everybody before me gave awesome talks about the future of Rust and how they use their tools to the benefit of the community. And this is not that talk. This also isn't a talk about the turbofish, although that's interesting in itself, and you should look into that because it's a beneficial tool to use. No, for me, I like to use programming language such as Rust to explore IVs or explore myself, and this is what I wanted to do with you. So basically, this talk came out of a workshop where we looked at this image. Does anybody know this image? Some people know. Yes, this is Escher. If you don't know this image, you're one of the lucky 10,000 of the day, because he's a lovely artist. He's Dutch, was Dutch, he's deceased now, and he made beautiful art. He's a graphic artist, and one of his most famous works explore the ideas of infinity and impossibility. And if you don't know it, you're probably going to love it. And this is a beautiful image that alludes to that sense of infinity, and probably you all will recognize some form of recursion. And if you look at the work of Escher, you might imagine that he's some kind of a mathematical genius, but he wasn't. He was just very talented and worked on his concepts of nature, and he was very much inspired by the Italian landscape, and his earlier work you can see reflected in that. So what I want to do with you today is to recreate this. So buckle up, because we're going to do that in a quick way. So I'm not claiming to be as talented as Escher is or was, but I know a trick, and I'm going to explain it to you. So let's look at the Rust logo and try to copy that, which is a problem nowadays, I guess, but we'll sort it out later. One way of doing that is by overlaying an image that you want to copy with a grid. And if you copy that grid, then you have a smaller task you can focus on. So for example, if we would copy the Rust logo and fill out the cell by cell, I would do the first one, that's the leftmost upper part cell. Then when quickly finished, then somebody else could fill in another part. So she has a little bit of work to do. And if everybody does its task, then at the end, in a slow process, the entire logo is copied. So this is called the painter's method, and it basically is an algorithm to copy an image that you already have. But the interesting thing is that you can change the grid. So if I squish the grid and instruct you to still copy each cell into the corresponding cell, you have a different image which is squished. Or if you maybe shear it or rotate it, if you still, as an artist, do your job of copying over your cell into your designated cell, we're winning. And this idea is central to what we're going to do. So what I like to do when having this concept of a painter's algorithm is to create abstractions that allow me to express that succinctly. So one of the abstractions I'm going to talk about is a box. So this is a box. It has 3 arrows, vectors, mathematical vectors, not the vectors you put stuff in. And the first one, read in this image, points where the origin of the box is. So this way you can manipulate the image by changing the origin. And the other 2 vectors basically say how the x-axis and the y-axis will change. So you can change the way the box is squished. So this is my implementation of that concept. It uses mathematical vectors. We're not going into the definitions of those. You can assume they are provided by some sort of crate. So because the IDs are mathematical, I'm using single letter names so we can use them all in. So A is the origin. You can change that to place an image in a position that you want. And the B vector is the x-axis. But although if you can change that, you can also point up. And the C is the y-axis of the corresponding box. Is that clear? So probably this is the difficultest concept in this talk. So if you grasp this, you're well on your way onto recreating the famous image of Escher. So my name is Daan. This is the letter D. Quite incidentally, it's a beautiful letter, not only because it's the first letter of my name, but also it has no symmetries. So if you flip it over, it will become a P. If you mirror it the other way, it's going to be a Q or some other letter that I can't pronounce. And we can use this to build up a language sorts of how we can manipulate pictures, basically. So one thing that what I would like to do is to turn it over. So it becomes like this. And what we're going to do is not figure out to draw the D. What we're going to do is we're going to figure out how to create a box from a given box that changes the letter. Is that concept clear? So I'm giving you a box that is the box you have to draw into, and you will give me another box that will flip the image that I'm drawing into. Does that make sense? So this is the original box on the left side, and what I want to produce is a new box that has flipped the image. So what I have to do is I have to align the origin, so the red arrow has to change, and I have to reorder the axis so that the image will be flipped. Does that make sense? So if you look at the screen and you tilt your head, the image looks somewhat the same. The only difference is that the red arrow has changed. But if you know a little bit of math and have studied vector algebra, you will notice that it is the sum of the original A, the origin of the original box, and the B, the x-axis of the original box. So if you sit down on your computer and translate this concept into a function that will accept a box and returns a box that is flipping the image, it would look something like this. And here again, the API of all those vectors is provided in a crate, so you don't have to really worry about it. But this is basically the task that we're now presenting to you. Given a box, produce a new box that changes the image in a way. Does that make sense? Okay. So if I would ask you to make a B, you can still figure out a way to create a box that will flip the image the other way around. Does anyone want to venture a guess? Okay. So again, if you have an original box, you need to create an image that will flip the other way around. The origin still has to move in a certain direction. It's the same as the previous image. And now the axes are changed a little bit differently. But basically, you need to negate one and keep the other. And this is the implementation. What I haven't told you is how these boxes are used. So if we look how flip box is used to create an image, the images in these algorithms are SVGs, basically. We're going to look at that now. So this is the implementation of how the flip box is used. If you look into the method body, specifically the most important rules is I will get a flipped box and I will apply that flip box, or will give that flip box to the painter, basically, or the picture. And what is a picture? Well, basically, a picture is a function, in a sense, that accepts a box and that produces a rendering. So what is a rendering? Well, a rendering is nothing more than an actual vector, a vec of things to draw, shapes. Those are lines, maybe polylines or polygons with some styles. How thick should I draw that line? And a number of those. So an image or an SVG basically is nothing more than a list of things that you need to draw. And what a picture is a function that accepts a box. You can see that as the canvas that you're allowed to draw on and to draw some specific shapes. Does that make sense? Some people or at least are nodding. So I will take that as granted. And this concept, like having a function that will accept a box and will give some shapes, is the central IDE. And because this is Rust, you have to fiddle a bit, or at least I have to fiddle a bit, with having a reference counter, because the picture or the painter needs to be passed around, and I don't want to worry about lifetimes, because sometimes they're a pain, but that will bite me in my ass later on. But basically, this is the concept is a picture is nothing more than asking a painter to draw something inside of a box. Okay. This is a toss. So basically, if I just flip the image or turn the image around, this is throwing it up in the air. And you can figure out a way to express that in boxes. Again, the original box is on the left, and the new tossed box should be this. And you can figure out that the relation between the axes is a bit obscure, but if you have a keen eye, you will see that the yellow right arrow ends at the sum of those yellow and purple arrows at the beginning. And if you do the math, you have to add them together or subtract them and halve them. But that's not really the most interesting thing. Now I see some of you worrying that is he going to talk the rest of the talk about these boxes, because that isn't really interesting. And no, I'm not going to do that. In fact, the next concept that we need is placing two boxes on top of each other. And because the code to do that uses helper functions, it doesn't fit on the slides. I'm not going to show you that. But I want you to focus on the concept. So like, if I would ask you to come up with a way to, if I give you a box, produce an image that has two boxes in it, you can probably figure that out. Like, okay, maybe I'm going to have a helper function that subdivides a single box with some fraction, and then maybe I need to shift the first and the last and give a tuple back of those two boxes. And that's exactly right. And that's boring, because those are boxes. And I lost connection with... and that's exactly the way you should do it. And you could do the same thing with putting images next to each other. You will create a function that creates boxes and puts them next to each other, and that allows you to express images that way. Is that clear? Great. So basically, what I'm telling you is that those boxes are helpful to explore the idea of creating images by expressing that in a higher order language. But these boxes, they're almost done now. Because if you want to express this image, and you know that you have basically a function that allows you to place images above each other, because that's the underlying concept that we just had. We showed the boxes, but there is also a function, basically, that takes a picture, or two pictures, basically, and puts them above each other. How would you express this? I have some time, so no worries. What was the? Yes, so you would compose those two splits. So if you have a function that accepts two pictures, then you can say, well, put this one above that one. And you have four of those, basically a quartet, that accepts four pictures. Then you can use those first two to maybe set them aside next to each other, and the entire image above each other. And that's exactly the same thing. So the implementation, forget about the signature, The implementation is nothing but put above each other the things that you need to be beside each other. So we have a picture northwest, northeast, southwest, and southeast, and you have to place next to each other, besides each other, both north images, and besides each other, both south images, and put those resulting images above each other. And this is magical, right? If you're still awake and you would think about what we're doing is we're expressing how to make a collage of pictures. And there's only, well, maybe one line if you have a code former that doesn't like indentation like this. And that's very powerful. And this is the power of expression. Like if you have the right abstraction that allows you to express yourself in a little amount of code. Again, if you have helper functions that allow you to place things beside each other with different ratios, then you can use that to express this image, the nonad. And if you think back about the square limit, that will allow you to maybe see, if you think in your mind's eye, that there's a roster that will allow you to express this. So again, I could ask the same questions. How would you express in code this way? And you will use these primitives to basically certainly express how to combine 9 images into a grid. And it looks like this. There are columns, and the columns have rows in them, and those rows are what you see here. It's not very scary, is it? And I hid the signature, but this is quite understandable. If I told you, here are 9 painters, let them paint in a grid, basically, then the instruction would be very clear. Like, you need to have a column of rows of things. Does that make sense? Great. Because it doesn't really take that much longer to express the square limit of Escher in this way. Because the only thing that we need is one way to overlay things. But basically, if you think back about the interface, what a rendering is nothing more than a bunch of things that you want to draw. So if you have a painter that can paint a D, and you have a painter that can paint a tossed D, then you just ask to paint them on the same canvas, and you're done. So basically, it is just adding the results of those painters, to a resulting vector. This is a fish. Now it gets interesting, right? I'm going to tell you how to draw a fish, but it's a bit like drawing an owl. So this fish, this is the real craft work. Like, it has stylus lines that allows you to see a fish, but it also has a lot of symmetries, and you will see later on that they will fit, interlock into each other in a marvelous way. So this is the real artistry, and I'm just handing you the result of that artistry. I haven't figured this out myself. This was given to me as well, and we'll talk about that a little bit later. So you're going to draw a fish, and the fish is the thing. But what we're going to do is we're going to create tiles. And this tile, you will notice the big fish present, but also there's some little fishes. So the things that we're building up to is a language that can express these things. So what are the ingredients that are used in creating this picture? Does anybody want to venture a guess?
I actually have a mic ready here.
Yeah, so somebody mentioned that. Maybe you can say it again.
The 2 little fishes are the same big one mirrored and then rotated at different angles.
Yes. So there's another suggestion.
Yeah, I was going to also say that you're probably going to tile this to make some kind of Escher-like.
Yes, so you can see here the tile that you're going to use to create the infinite pattern. That's exactly correct. So in fact, there's the big fish that's already given. It's overlaid with 2 little fishes, and the little fish basically is a toss-up of a big fish and flipped around. And then the last little fish, if you turn around enough times the fish that you have tossed and flipped, it will get the other fish. So expressed in code is not that complicated. So you have the big fish, you have the top fish that basically is a flipped fish that you had tossed, And you have the other fish, which is basically a clockwise turn, or if you turn 3 times that image, and you overlay all those things. So if you have the right primitives, expressing this image isn't that hard. You have to think about it, and if you do this yourself, you have to fiddle a bit, because you will see, there is some sort of relationship, I need to turn this a bit, but eventually we'll get this. And this isn't really complex code. Everybody in this room probably could have written this code, at least if you're guided by a great teacher like me. For the next question, there's another towel. I will spoil it a little bit. There is a toss in there, and probably everybody can see that if you have one fish and you turn it around enough times, you'll get the other fish, right? So again, this is a tile that's probably going to be used in the image, but it's not that complicated to describe if you have a fish. So if you flip and toss a fish, and you combine that with a turn, and you turn the entire thing upside down. So basically, if you have the top image, or the top and the left one, and if you turn it twice, you get the other part. And this is the beauty of the fish. Like, if you would have drawn a random fish, which you probably could, it wouldn't have those nice properties that the fins have right angles that fit together nicely, or the other one. So this is the real image, artistry of the image, of the fish. Does that make sense? Okay, we're almost there. So this is the side of the square limit of Escher. And if you look closely, you might see that it is subdivided into a square. And if you look at the, the bottom right square, you see one of the tiles just described. So that's awesome. We know that we can use that to express that image. And if you look at the bottom left side and you tilt your head, then you will see the same image you just saw. So those are the 2 basic instruments. And then if you have good eyes and you will zoom into the top right square, basically it's the same image, only smaller. So you're probably all familiar with recursion, and this is also what's used here. If you allow yourself to have faith and know that the bottom 2 are clear and that the top 2 are just recursive images of what you're working on, then that allows you to express this in code. And there's only one problem, because I've chosen, I've picked an abstraction that goes against the grain of Rust, and it has something to do with lifetimes and the function type that gets interpreted in a specific way. So if you were working in a functional language, for example, JavaScript, that would have a different feel to it, because what basically happens now is that we have the recursion inside of the painter's algorithm, and we need to explicitly call a box and then apply that box to the image. Whereas if you have maybe a less strict type system, you will be easier expressing this as just returning a function of the same type. Because the problem is that the if statement, the first block has a different type than the second block if you do the functional type. Or at least in my implementation, probably somewhere here could tell me how it should have done that. Please talk to me. But basically, if you have a parameter n that is 0, you just don't paint anything. And if you have a parameter n that is bigger than 0, you basically take the tile that you just described, turn it over, and place that in the quartet that we worked on. Make sense? That's basically the structure that it is. And this already is a complex image, but the implementation isn't that hard. So this is a corner. We're going to stitch those together in a little while. What you see here, again, if you squint your eyes a bit, you can notice a grid. And in the bottom right corner of that grid, there's the tile that we saw earlier of the 4 fishes next to each other. And if you remember and have a visual memory, you will notice that the upper right image basically is a side, right? It's just the same image as we had before. And if you tilt your head, then and you untilt your head again, the lower left image is the same side, only tilted. And again, we're going to use recursion here because the upper left one is just the same thing that we're drawing, only one stage deeper. Does that make sense? Great. So again, there's not a lot of code, and it's already a complex image. And what we're left is just assembling those things. And what we've done along the way is we expressed those primitives in a way that they are easily combined to form this image. Because if you squint your eyes again, you might notice that there is a grid. And this is the grid that we already created, the no-net that we created. At the center is the tile that we described, so that was the simple one. In the upper middle part of the grid, you will see that there is a side, and if you turn your head enough times, you will see them 4 times around. And again, if you look at the upper right, there's a tile that we've seen before, and if you turn your head again, you will see that those are copies of that. So basically, there are 3 ingredients. The center, which is a tile that we described, there are the sides and the corners, and if you turn the right things the right amount of times, you have the entire image. And this is the code to create that image. And again, Rust is fighting the abstraction here, but this is basically what the square limit of Escher is. There are some primitives that allow you to express that the code is nothing more than a no-net of 9 different pictures, and each picture in itself has a primitive tile that is turned around a couple of times and stitched together. Does that make sense? Great. So I didn't come up with this. These ideas come from a paper called Functional Geometry by Peter Henderson. He wrote that paper in 1982, and he revised it 20 years later, when it was 2002. These ideas are old, in a sense. What these allude to is that if you can express the concepts that you're working with in a way that allows you to combine them, you have a very powerful mechanism for describing complex programs in a simple way. Although far less visual than the instructions that I gave you, these concepts, for example, you can find them in partial combinators. It's the exact same concept. And what you invited to do is explore this paper, because it's a very nice paper. And if you want to explore these ideas yourself, there's also a workshop, a self-guided workshop that you can do, which you can do each step individually, guided by that work. So I would like to explain to you why I'm doing this. Because I did a workshop like this by Einar Host. He is a Norwegian software developer that is fond of this concept and can't stop talking about fishes. And a few years back, I was at a conference where he gave this workshop in Elm, which is also a lovely language. And I was mauled by this idea, and I created a workshop in Rust, which this talk is based upon. And last March, I went to a different conference, and I saw him again, and he gave the same workshop in a different language. And I attended because it's a lovely concept. And we started talking that the circle limit of Escher, which is also a beautiful work, you can't apply the same ideas to this image. And I didn't agree with him, because the idea is you have to combine simple abstractions into complex things. You can still do this for this image, but it's a bit different. And we challenged each other to come up with a way to express this image in code as well. So maybe next year, if there is a next year, I'm going to talk about that result. So thank you.
Thank you, Daan. Who's got questions about fishes or functional geometry?
Oh, yes, of course. So the last time I threw the box that far, it broke. There we go.
So why was there a suggestion that this one is not reproducible in such manner?
So if you look at the end result of the circle limit, it basically is on the flat plane. If you have an image and you shrink it a little bit and you shift it around on the plane, you can assemble those and stitch them together into this image. Whereas the circle limit takes place on the hyperbolic plane. And that is a different concept. So I'm actually creating code to re-express this. And what you have to think about is, well, this new geometry in the hyperbolic plane, whatever that means, how can you apply the same ideas of the functional geometry in that setting? Yeah, that's still a question. Yeah, so the suggestion is, can't you express those in matrices? Yes, in a way you're right. You can express some of the transformations as matrices, but there are matrices on the complex plane, but maybe that's a bit too technical to shout out over an audience. If you want to discuss that, just come around and we'll talk about it. Other questions or suggestions? There are a few.
Oh, there. Oh, fun.
Thank you. Could you go back for a second to the slide about the toss?
About which one?
The rotated box.
Oh, the rotated box. Yeah, sure.
Yeah. It was, yeah, in the beginning. Yeah, here.
This one?
No, not this one.
This one?
No. I think it was also at an angle.
Okay, the toss one.
The toss one, yeah.
Yeah, sure. This one.
Yes,
yeah.
Indeed. So I actually wanted to ask, this is essentially just a rotation from what I see?
Yes.
And you mentioned that you also scale it by a half.
Yeah.
Why do you do that scaling? I mean, I do get it for the end result, but yeah.
Yeah, so the basic answer is the fish that you saw has properties that fit nicely with this toss. So if you see this fish, and you toss and flip it, then it will align nicely.
I see. Okay. Yeah, makes sense. Thanks.
Yeah?
Yeah.
There were still another question.
Does it work?
Yeah, so the box is there, so you'll get it afterwards.
Nice. So thanks for a nice presentation. It does look like a fun thing to do, especially with multiple programming languages. But looking at the snippets, I have to wonder if Rust might be particularly unsuitable for it. You had to wrap everything in reference counting. You had to add a lot of type annotations, traits, and so on.
Yes.
It probably would have been much easier to use a different language. So I wonder if there were also benefits, or if you just wanted to use Rust because you wanted to use Rust.
Yeah, you're entirely right. So I don't think Rust is, or at least my Rust powers are a nice fit for expressing these ideas. But what I wanted to do was challenge myself. Can I express those? And like challenge yourself to do a task and see where Rust will lead you is an interesting exercise in itself. But you're right. At least to my knowledge, at the moment that I created the workshop, expressing those ideas was a bit ugly. Like the signature type with a lot of different images isn't very fun to see, and that's to my understanding is because their functional types are different because although they look the same. But if anybody has ideas to express this more singularly, that would be interesting as well. So I don't think you can say that Rust is a functional language, but it has some functional aspects that will relate to this as well. Yeah. Does that answer your question?
Yeah.
Cool.
He was before.
So just one question about the circle limit. Is it like so it's on the hyperbolic plane, so the straight lines are not straight lines, I guess, but is it is the reprojection of the square limit on the hyperbolic plane? Or
no.
Is it differently?
It's different. So the fishes here are fishes as well. They share that, but the relation between the fishes is different. So, and I can understand where you're coming from, that the straight lines aren't straight lines, but in the hyperbolic plane they are straight, but this representation
because of reprojection again.
Yeah. But the symmetries of the fish basically are different than the symmetry of the fishes in the square limit.
Yep, thanks.
Just as a suggestion about you were mentioning the how to express this in Rust. Have you, when you were implementing this, have you looked into rather writing multiple types and attaching methods on those types and having each method return a different type? In a way you can chain it, like in a iterator-like way, where with adapters and things like that.
Yes, I haven't done it in Rust, but they're like the concept. Basically, the concept is you want something that combines nicely, so that you can express these complexities with simple mechanisms. And there are multiple ways to do this. You can do this in Python, which also has functions, but you can also do just classes that then will have a class, a tree of classes that have responsibilities of drawing objects. So there are various ways to do this. And the interesting is that the idea can be applied to different languages and different language models. So I haven't done that in Rust. I haven't done it in other languages, but it will be interesting to explore your idea. Yeah.
Anyone else?
Where?
Yeah, I wondered, did you ever try to do the reverse? So set up an empty image with repetitions and draw on it, so you can figure out, okay, this is a nice shape to create a fish or an owl or whatever.
I haven't, but there are people, especially for the regular plane, the flat plane, that do this. There's I will tweet a link to a project that does exactly this. So that allows you to take a symmetry of the plane, so that will tile an image, and then it allows you to draw things on your tile, and then it gets repeated, which is exactly your idea.
Cool.
Yeah.
Thanks.
All right, that's looks like no more questions. Thank you, Dan.
Thank you.
All right, so that's all of our talks for today. Thank you for sticking with it. I hope you liked it. We would like to have all our speakers here on stage. So
yeah, that's going to be a logistical nightmare, isn't it? Yeah, I'm sorry. Maybe we should have thought of this a little bit sooner. I'm sort of assuming that everybody now has to get up, but
it's not too bad, looks like. Just as a token of our appreciation for your preparation and sharing your
so thank you all.
Knowledge and imagination with us today. Cool, and did you have the other?
Yeah,
So one more.
I also want to invite Rik Arends.
Yes,
down
who is
to the stage.
Basically the driving force between today, behind today. So thanks, Erik, for putting all of us and everything here together. And we have a nice present for you as well.
So Erik has been an absolute superstar in organizing this conference. I mean, it's nice for Dirk-Jan and me to stand up here, but the amount of work that went into organizing today is absolutely tremendous. So there's been a lot of sleepless nights and a lot of phone calls and a tremendous amount of emailing in order to make this all happen. So thanks very much. Give another big round of applause to Rik Arends.
And of course, we should mention again, thanks to all of our sponsors, FutureY in particular, but also the other sponsors for participating in making this event possible. So, it's almost time for drinks. We have a few more things. So if you want to be involved in the Dutch Rust community and attend events in the future, be sure to subscribe to our meetup community, where we will announce further meetups. I don't know, we don't, I think, have a concrete plan for the next one, but that's why you want to subscribe. For those people who were invited to the dinner, please be ready at 6, around 6 to leave. So the drinks will be between 5 and 6. I think that's all. So you're... we'll see.
No.
We'll see what we can do.
So, who thinks this is a good idea? Maybe we should do this next year. Raise your hand. Woo! No pressure. Okay, yeah, we're gonna find other people to organize it. No, seriously, this was super, super fun. Thank you all for coming. Hope to see you again next year, or at some smaller venue somewhere out in the country. Thanks again. Everybody.